Hello. Hello.
Hello, good morning.
Good morning. I thought I was just on my own. Hi. Can you see me? Because
Yes, I see your board and now your face. Good morning.
Good morning. Right. So, okay. Wait a second. Maybe I should use a filter. Filters. Wait, I erased the board. Hope that's better.
Hi, Suzanne. This is Barış.
Hi, good morning.
Good morning. Hi. Günaydın Zafer Hocam.
Günaydın.
You want me to try that everything is okay with the slides? Oh, I guess should be straightforward, right?
Barış, are you in charge of this?
Yes, Hocam. Yes, Suzanne, you can share your screen. Maybe we can leave the screen with your slides on.
Right. So, share screen. It's okay.
No, looks fine. Yes.
Okay. It's completely fine. Thanks.
But maybe for the introduction, I stop sharing and then we see that it's just a few seconds. Okay.
Okay, sure.
So the previous meeting you could do in presence, the previous edition of the KOBİT, or was also online?
The last one was also actually the one before we were online.
Was it 2021? Yeah, okay. Mm. And this is a bit like the annual meeting of the quantum optics.
Exactly. Actually, originally the group, I joined the group later, was a quantum optics group.
Mm-hmm.
And it extended to quantum information, quantum computation. So it is basically our Turkish quantum information and computation community, including quantum optics.
Right, good. Mm.
By the way, Barış, Nadir, do you have something to say before we start at 10:30?
Actually, I'm sorry, my voice is echoing, I guess. Okay, it should be fine now.
Yep.
So at this point, I guess we don't have anything to say. but I will make a couple of announcements at the end of this session before we continue our discussions and break in the Gather Town. So at the end of this session, I'll make a quick introduction to Gather Town and a couple of announcements before we proceed into the break. But at this point, I guess there are no general conference announcements.
Maybe I can add some, if there are questions coming in from the YouTube channel.
Yeah, okay. I have just received the message from Onur, so I will be waiting for them as well. Okay.
Perfect.
So Suzanne, how's everything in Ulm in terms of COVID restrictions and all? So you are back in the offices, I guess?
Yes, we've been back in the office for some time, right? But the format of the winter semester is mixed. So we are having recorded lectures together with some live discussions with the students. I mean, in physics works because somehow the groups are relatively small. So actually is maybe even more productive than the standard way of teaching. So that's working well. What is being more complicated is really the running of the group, in the sense that there are quite a few limitations for gathering. So we cannot be the whole group together for anything. Yeah.
I see, yeah.
So discussions, I think in our biggest seminar room, we can be like 10 of us, keeping the distance. So it's a bit, tiring, right? Because it has lasted for so long.
Yeah.
But hopefully the worst is over. But now with Omicron, we are starting to have some positives closer and closer.
Yeah, I see.
Yeah, so my hope is for the next summer semester. Hopefully.
Yeah, hopefully. Yeah, I see. Have you been tested positive anytime?
No, but I tell you, somebody a few doors away was testing positive. So I think with Omicron, probably we are all going to get infected.
Yeah,
so,
I think so.
Let's hope that with all the vaccines and so it will be mild. Yeah.
Yeah. I mean, I think it has been mild for everyone with vaccines. I mean, who has been vaccinated before they got the Omicron. I mean, as far as the people that I have encountered who got the Omicron with vaccines, they only have mild symptoms, and then they got over the illness quite fast, I guess. But in any case, you never know, I guess.
Yeah, you can be unlucky for whatever reason, but fingers crossed.
Okay. Okay. Hi, Steve, by the way.
Morning, man.
Good morning. How's everything?
Yeah, good. It's early, but I'm working from home today. So
yeah.
Hey, Suzanne.
Ciao, Steve.
Good to see you.
Okay. So Zafer, maybe you can take it from here, and then we may start. I guess it's 1 minute to 10:30. Okay. So I leave it to you from here. So see you.
Okay, thank you, Pyrus. So, hello everyone. Good morning, especially our colleagues in the West. It is quite early for them. Thanks for joining us. Welcome to the 6th Quantum Optics and Information meeting. Unfortunately, we are online one more time this year. There is a Turkish song actually with lyrics something like "Let this be the last. This is the last." So let's hope that next time everything will be face-to-face, physical. I'm Zafer Gedik from Sabancı University. I'm the chair of this session, where we have 2 talks. First, our plenary speaker, and then we will have an invited talk. So the first one, the first talk will be presented by our plenary speaker, Professor Suzanne Huelga from Ulm University. Professor Huelga received her PhD from University of Oviedo. She was a postdoctoral researcher at Oxford, then at Imperial College. And following her positions at Oviedo and Hertfordshire universities, she moved to Ulm, where she has been doing her research studies more than a decade. Her research interests include several topics in open quantum systems, quantum information, and quantum optics. And her studies in quantum networks, biomolecules, and quantum metrology are among the most cited ones in the field. Like her contributions in quantum networks, she is also a well-known figure in quantum community network through her collaborations, especially in Europe. Today, we are happy to guest her to learn about some recent developments in quantum phenomena in biology. The title of Professor Huelga's talk is Coherent Effects in Biological Systems, from reduced models to numerically exact simulations of dynamics and spectral response of pigment-protein complexes. So, please, Suzanne.
Many thanks. Now having problems to open. Wait a second. From the beginning. Okay. Hope you can see it.
Yes,
so many thanks for the kind introduction. And it's a pleasure to actually open, pleasure and honor to open the conference to present you group work that has been done in the group in roughly around the last 10 years. So I thought that it may be instructive to have a sort of historical perspective to see how the thinking about this type of coherent effects has changed, and also to show you what are the pending and then the outstanding issues. So I've organized the talk thinking that there may be people in the audience that have never heard about this actually, so that you will get a sort of overview. So the first thing we should discuss is, because talking about quantum effects in biology may sound a little bit pretentious, right? So we'll see what sort of systems are we talking about, and choose then as a case study the light harvesting processes involving photosynthesis, and discuss the type of experiments that have been performed and led to actually the word coherent be brought to this context. Specifically, one wording that all the time accompanies any discussion is the possible presence and the possible observation of long-lived coherence. So we need to understand, what does this mean? What is long with respect to what is short? And then the core of the talk would be analyzing or putting forward a Byronic model for the type of systems that are at play, where you will see how we evolve from toy models initially to try to draw some fundamental principles, to now being able to deploy machinery developed in the last years to tackle realistic environments. So in a cartoon like this would be the broad scenario. Nature has had time also to develop an incredible architecture to be able to harvest energy from sunlight and convert it into stable forms of energy that can then be subsequently used in order to produce food, ATP. So plant, bacteria, and algae have a photosynthetic apparatus whose essential building blocks are membrane proteins, like the ones I tried to depict, borrowed this picture from a textbook. So in green, you see a network of highly absorbing molecules that are complex with a protein scaffold. So this combination is a pigment protein complex, whose role is being able to convey photons that are being absorbed from the sun to a reaction center where charge separation will take place. So what is significant is that despite the photon absorption may be highly inefficient, while a photon is captured, and especially in low light conditions, so when it's essential for survival to keep the light in the system, then the efficiency from photon absorbed to charge separated is 100%. So we are talking about then the primary steps in the complex process of photosynthesis, and specifically the exotonic energy transfer that takes place across antenna complexes on a picosecond time scale. Now, the reaction center is a relatively well-conserved architecture across species, but depending where the photosynthetic system is placed, depending on the natural conditions, then there is a large variation of antennas that have been developed. But there is one that belongs actually to a rather, probably from the biological point of view, not that relevant bacterial organism, is the famous Fenner-Matthew-Olson complex, which is simple in biological terms, given that it only involves 8 bacteriochlorophyll, so 8 pigments embedded. So these lines you see around depict alpha helices and beta sheets that are the protein cage where these bacteriochlorophylls are placed. Right. There are 2 varieties of this complex, and the S2RE one was actually the first pigment protein complex that was analyzed completely via X-ray crystallography. So this is, if you want, a little bit the James Cummings model of quantum biology, in the sense that we have a very significant body of spectroscopical information to be able to kick off doing an analysis within the theoretical framework of open quantum systems to try to understand why is it possible and what is happening for actually having a nearly 100% efficiency energy transfer. So one thing you should keep in mind, because this will be relevant when we try to put everything together, is that we have a spectroscopy for this complex, different forms of linear spectroscopy ranging from absorption to fluorescence to different forms of dichroism, plus the X-ray information, to actually being able, with variations, these numbers have been readjusted over the years, but let's say that we can put at least initial numbers to what would be the energies of the pigments and the corresponding strengths of the couplings, dipolar couplings that will be triggered in the moment that there is a photon absorption, right? And then the network starts to talk to each other via a dipolar dielectric coupling, right? But one important thing to keep in mind is that the numbers we are putting here really come from trying to make a fit to what is experimentally observable. Among that observations are also fluorescence line narrowing and other type of measurements that characterize the spectrum of the fluctuations. So we have some initial guesses for what is the possible spectral density. So the type of fittings indicated here, that will be our initial starting point for writing up a Hamiltonian, right, come from this combination, and normally the underpinning theoretical model involves a smooth, coarse-grained spectral density. I will elaborate on this later. But let's say that for the moment we have an initial set of parameters with combined origin, that would allow us to say, okay, in the first instance, I really write down a Hamiltonian involving some site energies for each pigment, and then I can also write down an interaction part where I can put some numbers for the value of this electronic coupling, right? So if you think about the network of pigments alone, right, disregarding both any possible vibrations coming from the protein scaffold together with internal molecular vibrations, right, I will consider the Hamiltonian characterizing uniquely the electronic degrees of freedom. And I will call excitons the eigenstates that will come up from diagonalizing this interacting Hamiltonian. Okay? Depending on the strength of the coupling, you can imagine that the excitonic states will be more or less delocalized over the network. In the specific case of FMO, the delocalization is actually not that large. There is two pigments, 1, 2, that are strongly coupled, right? And at most, the most delocalized excitons covers about 3 pigments. Right. So the spectroscopy of FMO was actually done in '68, as far as I recall, right? And let's say that the possible involvement of coherent effects in the transfer, right? Despite very, very seminal work already in the 20s, a little bit of wild speculation, I would say that the type of results that really triggered the attention on communities that were not working in photosynthesis, like our community, were possibly the experiments of Graham Fleming and his group, and subsequently by Greg Engel, who was a postdoc in Fleming's. Of course, these things don't come just spontaneously. This is the result of transferring all the machinery that have been developed in the infrared now to the visible, so that optical transitions can also be addressed. So to all the battery of information that we have from linear spectroscopy, now we add the one that is obtained in a different manner. A different manner that maybe given that quantum opticians dominate the audience, I think you can get the gist of it if you think of a Ramsey interferometric setup, right? These are experiments where, if you think about a common ground state, think only of a dimeric system, right? Whose interaction will yield to the formation of two excitons, E1 and E2, with a certain gap, right? So now think about the possibility of preparing by external irradiation a coherent superposition of excitonic states. So in a Ramsey setup, that would be applying a pi over 2 pulse. So now you have a part of the experiments that creates coherence. You let it evolve during a free evolution time, and now you have a second pulse that will read out that coherence by means of yielding a population. Okay, this is what you do in a typical interferometric set. So you see that the signal that we will get, should the evolution be completely unitary, would be a sinusoidal signal, typical indication of an underpinning coherent evolution, right? Now, if we think about performing this very same experiment in a situation where we have noise in the evolution, think, for instance, of having pew dephasing, then the amplitude of these oscillations will be reduced. And after some time, it may be that we are holding just a purely mixed state with no coherence whatsoever between the excitonic states. Okay. So here we can already identify what do we mean for long versus short-lived coherence. Superpositions in monomers involving only the ground and the excited state are done in a few femtoseconds. However, oscillatory signals that were assigned to excitonic superpositions were considerably longer lived, even extended towards the picosecond domain that, remember, is the typical time scale covering energy transfer in FMO. So, of course, the situation in reality is more complex, right? The type of nonlinear spectroscopy, nonlinear means nonlinear in the number of pulses, involves in it's a generalization, if you want, of pump probe experiments, involves two pump femtosecond lasers with a separation tau, the coherence time, right? Then we let the system evolve for a waiting time, capital T, and then we'll have a detection time, controllable, right? Okay, the point is that given that we have these time separations between probe, this the variable detection time T, then it's possible to actually make Fourier transformations of those time variables in such a way that we can present the spectrogram in a 2D form in such a way that we can make a correlation map in between the excitation frequencies and the detection ones, right? So if there is coupling in between the pigments, right, then what can happen is that there can be in our spectrograms features where energy is absorbed and emitted at different frequencies. So this is a signature of coupling and allows, among other things, detect in which way energy is being transferred across the complex. Maybe just that you get a picture of what type of information this spectroscopy allows you to get. If you then think about varying the time in between the two pulses and the detection one, and focus your attention on one of the features, for instance, one of the cross peaks, if you follow what is the evolution of a selecting regions as a function of the waiting time, then oscillatory signals come out, right, which in particular may involve an oscillation at the frequency gap of the exciton separation. So then the initial observations, if you want, is that there are oscillatory features in the 2D signal from different complex, not also FMO, but also reaction center and the units present in certain type of algae, lead then to suggesting, you see that I'm being conservative with the wording, right, that given that this coherence can be observed on times that are relevant for something important to happen, in this case, excitation energy transfer, there could be a potential relation between the presence of that coherence and biological functionality. So this is what we want to scrutinize. Let's say that we will try to see first, how is it possible that can happen? So is it the case that we can really see that indeed long-lived oscillations could be observed? Second, what is the microscopic underpinning? What originates them? And then finally, see whether we can actually link that with some connection with actual biology. Okay? So there is already even a back of the envelope calculation that you could do, saying, well, actually, I'm not that surprised that there could be a difference in between the lifetime of oscillations involving ground excited versus excitonic ones, right? Because here, forget about the 800, 850, because I wrote for a different complex, but think about the general Hamiltonian where you have side energies and then an excitonic coupling, right? And now I diagonalize it coming with my excitonic states, right? If initially I have a given dephasing rate for the uncoupled systems, right? If I now make the admittedly far-reaching assumption that if I would be able to describe the dephasing of an isolated chromophores via a master equation with certain rates, right? If I make the assumption that the dephasing of the excitons will be ruled by a master equation of the same functional form, now with different coefficients, well, a back of the envelope calculation tells you that as a result of the delocalization due to this coupling, then you can have an effective reduction of the dephasing for the excitonic superpositions. So that could be, you know, a guiding idea that maybe as a result of the coupling, that's not impossible to happen, right? But take into account that we would like to even go further, right? So we want not only been able to explain how is it possible that there could be significant coherence between excitonic states in the presence of a possibly very aggressive vibronical environment. But we would also like to say this coherence should be able to facilitate something. Very much in the spirit, you will conclude the story saying, well, very much like I have 100% fidelity to perform qubit teleportation if I share an EBIT of entanglement, we would like to say something like, okay, this process will happen with this or that efficiency if and only if there is coherence in the system. So this is something tricky, very nice, and still to be done, right? But for the moment, I think we can understand what is going on microscopically for possibly having long-lived coherence in the systems. Right. For us, given that I adopted the historical perspective, let's say that when we heard about the experiments of Fleming and his group, we were at that time really trying to understand under which circumstances was advantageous to have noise in the system to perform information processing. And we knew at that time that, in fact, if we wanted to have steady state entanglement, right, it was advantageous for the system to be open. This is something that is now mainstream, right, but in 2002 was still a little bit of an exotic result. So somehow we have the hope that maybe in these complexes, something like that, a productive collaboration between coherent and incoherent interactions would be the reason why we could have this long-lived coherence. Okay, so what would be your starting point if you have a background in quantum optics? You will say, well, the first thing I will try to do is really divide the universe into two pieces, identify my system of interest with the network of chromophores, dipolarly coupled, and I put in this blob in orange everything else, all the vibrations in the world, okay? And I make the assumption, right, that the noisy processes that will be affecting these coherent dynamics will be a dissipation term that will make excitons relax and also some residual pure dephasing. So let's see how far we can go with this very simple model. Right, so we identify as our figure of merit what would be the amount of energy that is being transferred to the reaction center, modeling this transfer process as an incoherent transfer from the lowest lying exciton into the reaction center. Then what we obtain is that if you would have a network that doesn't exhibit any dephasing, so if in the case that I do a simulation in the side bases, take into account that the only noise present would be pure dephasing, right? The information we have is that physically the source of noise is actually local per chromophore. There doesn't seem to be signatures from molecular dynamics of spatial correlations. So this is a calculation with a master equation formulated in the side basis and computing what would be the excitation probability in the reaction center. So we are measuring our ability to efficiently convey energy as a function of the dephasing rate. So If the system is not noisy, this network will be highly inefficient. You will tend to delocalize the excitation, right, in such a way that some of the delocalized IV states don't have any overlap with the pigment with the lowest energy, or not the lowest energy, the closest to the reaction center. And as a result, roughly only 50% of the excitation will reach it. Something I didn't emphasize is that there are no signatures of having more than one excitation at a time, right? So we have, from the beginning, the simplifications that we can do the discussion in the one excitation sector within this picosecond time scale. Should you increase what is the level of dephasing, what you encounter is that actually it's possible for certain optimal dephasing rate to reach 100% efficiency. So perhaps not that unsurprising nowadays. What is clear is that we need a combination of coherent and incoherent processes at play in excitation energy transfer in such a way that there is one physical mechanism that allows for unfavorable configurations to emerge. So the behavior that we encounter if we plot what is the probability to convey energy to the reaction center as a function of the dephasing rate is this typical non-monotonic curve where we have an increase in the transfer, right? If we modify, upgrade the dephasing, right? Until reaching a region of optimality, and then should you continue increasing the noise rate, then you will effectively localize the excitation in a given site. So there were independent results at the same time by the group of Alan Aspuru, and now this type of phenomena is normally referred to as NAQT, so environment assisting excitation transfer. I think for quantum opticians, it's easy to understand that indeed that's something that can happen, right? And a very nice textbook demonstration happened a few years ago in the group of Rainer Blatt and Christian Brott, where they consider an array of, I think they were like, okay, a 10-qubit network, and you see how they could reproduce experimentally nicely this behavior of the excitation transfer as a function of the dephasing rate. So that was, let's say, the first. We can still keep even within the back of the envelope calculations. The first results pointing towards the fact of having a combination of coherence and incoherence at play in this type of complexes. The validity of the type of master equations that we have used, should they be obtained ab initio, you know that will rely typically in the validity of von Markov approximations, right? So having really being in the presence of a reservoir that should be as close as possible as delta correlated. If we look at what is the information we have concerning the spectrum of the fluctuations of the phonon bath in these complexes, you would be a little bit stressed to see what happens, and is that the environment is very structured, right? Moreover, the presence of underdamped modes, that can be many, despite the coupling to each of them individually may be small, given that we have many and they can extend over large values or high frequencies, makes really the typical assumptions for the validity of reduction descriptions, sitting on the fence, right? So we need, if we want to make any connection to actual photosynthetic complexes, we need to move forward and being able to predict what sort of behavior should we expect when we include the complexity of the phonobath, right? And moreover, take into account that reading out properties concerning the specific details of the transfer from spectroscopy is far from trivial. So for our theoretical apparatus to be predictive, we need to account for the spectroscopy as well. Right. So then the next work we did was trying to incorporate some structure into the bath and take advantage of the type of numerical methods that have been developed to tackle many body physics in a numerically exact manner. So I'm just controlling how I'm doing with the time. So let me present you the first analysis of this type, where actually consider a dimeric system, right, with a type of parameters that were inspired by the first and second chromophore in FMO, that are the ones that are strongly coupled. Right, so if we write down what would be the Hamiltonian, I'm using a parameterization where I will couple to the displacement of a harmonic oscillator bath in a way where typically you will write the complete constant if you want to compare it with the physical chemistry literature in terms of what they call the Juan-Riesz factor, SK, right? Then we have that G is equal to square root of the Juan-Riesz times the frequency. Okay, so one way to get intuition about what can happen in the presence of a dimeric system that is dipolarly coupled by this interaction and is also coupled locally to a phonon bath with environmental operator being the global displacement of these many modes, right? If you rewrite the Hamiltonian, right, in terms of excitonic states, then you see that the role of the environmental modes looks very much like a driving term that could then, should it have spectral features in the vicinity of excitonic gaps, can act as an element that may regenerate the coherence that is lost as a result of the effect of all the other vibrational modes that are far from resonance. So in a very cartoon manner, think about of an spectral density, right, that exhibits a very sharp spectral peak due to the presence of an underdamped vibrational mode in the vicinity of the excitonic transition, right? So if we prepare an excitonic superposition, remember the effect of a first Ramsey pulse in an interferometer, right? Then should the evolution be unitary, this will simply precess at the excitonic frequency, but in the presence of local dephasing in the exciton bases, we will now be thermal relaxation of excitons. This will try to decay, right? However, if we have a mode that is close to resonance, we can then imagine the action of this mode as really trying to drive this transition coherently and competing with the relaxation component of the rest of the modes on the excitons, right? So we could expect that indeed the presence of these underdamped modes in the vicinity of the resonance may allow the beating to persist longer. You can say, okay, that's all blah, blah and cartoons. So what did you obtain? Again, we wanted to escape from reduced formulations. So from formulating reduced master equations for the excitons, right? In order not to be ransom for all the unavoidable approximations that one would have to make, right? In a situation where the microscopics is still relatively not as well characterized as in a quantum optical scenario. Eh? So for that, what we did is taking advantage of methods that implement density matrix renormalization techniques, right? And use an efficient procedure to actually map out our dimeric system coupled to this complex phononic spectral density, right? Made up of one that has an experimental ground, right? And then combined with essentially a very sharp Lorentzian peak. The important thing is that it's possible to unitarily transform now this initial configuration into a 1D configuration where the coupling between the new effective modes is only happening at the level of nearest neighbors. And this is an architecture that is friendly for a simulation with the NRG. So then the results that we can obtain are numerically exact. Eh? And this is what we get for what would be, should it be accessible experimentally, right? This is a fully theoretical analysis. We compute the evolution of the whole world, right? Electrons and photons, right? And then we trace out the phononic path and examine what are the properties of the excitonic density matrix, where you can see that indeed, in the presence of an underdamped quasi-resonant mode, we are able to sustain the oscillatory behavior. These were simulations done at Lotte 77, but the interesting thing is that we can also show the persistence of oscillatory behavior also at room temperature. So then this analysis suggested that actually the key word may be here the formation of vibronic coherence as a result of having the possibility to have coherence at two levels, one that results from the excitonic degrees of freedom, and the second one from the interaction of those with selected vibrations. So the model was actually successful in describing experiments with artificial systems. And these are two references where specifically the theory was used. And in parallel, let's say that the same type of theoretical framework was also used to analyze the now not energy, but actually a process that may even be more relevant from the biological point of view, that is charge separation in the reaction center. So both the group of Rick Van Grondele and the group of Jennifer Ogilvy observe the observation we have for the efficiency of the charge separation were consistent with the identification of modes in the vicinity of the resonance of the special pair. Right, so you may see reasons to believe that indeed there could be long-lived coherence in pigment protein complexes. However, there is not yet a complete agreement, not in the presence of oscillations that I think everybody believes, and I think you only need to enter into a laboratory for these spectroscopies to realize that there are oscillations everywhere. But the issue is to which exact mechanism they are attributed. So in particular, this is a penis, but actually I may not have included right now. There is even a more recent reference in Science Advance led by Dwayne Miller, where they argue strongly on the purely vibrational origin of the oscillations, saying purely excitonic coherence will be very, very short-lived, and really what we are observing is mainly oscillations that are due to contributions from the ground state. So oscillations between the ground state and the first phonon, which obviously has the same splitting as the excitonic one. Okay, so let's try to contest that and arguing that no, that may not be the end of the story, because take into account that we started including a little bit of the complexity of the phonon bath, but far from really addressing what is going on with the true spectral densities. So then these are results that are currently under revision, and you see that there is a bit of a gap in between the results I just explained, right, and the ones I'm going to cover in the last 15 minutes. And it's really due to the fact that we didn't have tools to tackle what is going on if we want to include all those modes that are happening in the high frequency region. So what we've done now is took a while to really be in a position to say, okay, there are 55 underdamped modes with a line width of about 1 picosecond. And we want now to be able to include them all in the simulations and even being able to move to room temperature. So, and we want to compute spectroscopy. We may still do the calculation of propagate everything, trace out phonon, see how does the excitonic density metric look like, but also we want to be able to compute theoretically what is actually measured. And those are spectroscopy being linear or multidimensional. So we consider then two model systems, which are truly dimeric actually. One is the water-soluble chlorophyll protein, which is another very well-studied complex, irrelevant biologically, but a nice toy model for theoretical studies. And another one is a very relevant system for biology because it's the special pair in bacterial reaction center. So if you ask biologists, they think that if any optimization is happening, it's much likely to happen for charge separation than for energy transfer. Okay, so the point is that if we look at the spectral densities, we are considering one dimeric system where the splitting is far away from the high energy tail with many underdamped modes versus the reaction center whose energy splitting falls in the middle. So what do I mean with this energy splitting? This would be the one that is computed to fit linear absorption in the case where the spectral densities are coarse-grained. So this is a value that has been then adjusted in such a way that with this spectral density and that gap, we reproduce linear spectra. So like the table I showed you at the beginning. Okay, so actually, to understand what is going on, we can even do simple perturbation theory to understand what sort of renormalization effects will happen as a result of the presence of these many modes. What we obtain is that the splitting will change, very much like lamp shifts are happening in quantum optics, and the new effective splitting that will concern now bibronic states, right, can actually be smaller than the previously estimated or larger. What is the significance of this? Well, the significance of this is that the way to determine what are the values of the couplings I introduced in the system Hamiltonian are derived from here. And if this is different from that, and if this is different from that, then what happens is that the new bare electronic couplings that I will consider now are different from those initially. In particular, the electronic interaction can actually be larger. And this is very significantly for the interpretation of the oscillatory features in 2D, because one of the standard arguments is that the interaction between pigments is not strong enough. But the point is that there is a very large uncertainty in what that value can be. In particular, can be significantly larger. So definitely the issue of ascribing oscillations to being purely vibrational or being of bibronic origin, I would argue that is still to be confirmed. But definitely there are reasons to believe that when we do a full analysis, including the complete spectral density, we cannot just simply smooth out this part without paying a very serious price. So just to illustrate how powerful the calculations can be, these are actually results for exact absorption spectrum, right? That, I mean, even, let's say, to be more convincing, we use not only our second generation TEDOPA, but in fact, we use hierarchical equations of motion to be able to have a different numerically exact technique, right? And what we can see is that in green, you have actually the spectrum that has been measured, right? What we obtain is that it's possible, if you look at the diagram we have in C, we can fix it completely, right? You see that the agreement is really good with the curve in black when we include the 55 modes. And should we start coarse graining, you see that if I now consider 40 instead of 55 or 20 instead of 40, you see that the distance and the shape in between the two main absorption peaks is modified. So in fact, should I repeat the calculation of the absorption spectra exactly with the initial estimation for the excitonic gap, I get it totally wrong. So the effect of this very complex environment is absolutely crucial to be able to account for the spectroscopy. And we did a similar analysis for the special pair in the reaction center, where actually the effects as a result of having a larger electronic coupling are even more starking, right? And then we can see when analyzing both signals in the cross peak of the actual spectral response or doing the analysis of the properties of the excitonic density matrix, that we do observe oscillations in the excited state manifold which have an electronic component and that live on a picosecond time scale. So by means of using numerically exact techniques that can now include the full complexity of the spectral density, we argue that the contributions of the purely excitonic coherence to the global 2D response may have been underestimated. So the debate is still on, right? And one of the take-home messages of the talk is that in this type of complexes, connecting dynamics and spectral response is not a trivial matter, in the sense that you are building up modeling, right, relying on parameters whose estimation is model dependent, okay? So therefore, in order to unambiguously link an observation, for instance, in 2D spectroscopy, with an underpinning dynamics, right, then we need to be able to have methods that allows us to simulate the actual spectrum of the fluctuations. Right, so even if you would believe that what I said so far makes sense and that pigment protein complexes seems to be a nice example of a composite interacting system exhibiting long-lived bibronic coherence, we still have pending the big question of saying whether this coherence is actually the responsible for some enhanced function of any form. And this is still pending to be answered satisfactorily, but in my opinion, the framework of thermodynamics is probably one that is particularly well suited to answer whether there is any connection between coherence and function. So just very briefly, ultra briefly, let me just tell you some initial work we did in that direction, that is thinking about the pigment protein complex as a thermal machine operating in between two baths, right? The thermal bath from which they extract excitation and the phononic one where they dump the excess energy. Well, what is interesting to see is that depending on whether or not you include localized vibrations, right, you can have a performance of your thermal machine, right, that exhibits larger or smaller efficiency depending on whether the localized modes are present. In particular, the energy, we can define an associated power, so energy population per unit time, right, in such a way that we compare now the power delivered for complexes where I will have, let's say, a smooth spectral density versus one that includes localized modes. Actually, the power in the coherent case is enhanced. So let's say to link function and coherence in the context of biology, we will need something like that, being able to identify specific tasks whose performance is unambiguously enhanced by coherence, or facilitated or made possible at all. So that would be the loop we would like to close, right? So far, you've seen that in the light of the latest result, I would argue that the analysis is quite solid in here. The issue of identifying an ambiguous relation between enhanced function and coherence would have some indications. So the view of having these cooperative effects between noisy and coherent dynamics seems to be suitable to think about these systems. And even if we forget completely about actual natural complexes, I always like to show this slide telling that what is the answer to, are quantum effects relevant for biology? Maybe not, right? But very much like flying objects, right, do fly and they don't do it like birds, we can exploit biology to really identify basic design principles that can be harnessed in artificial scenarios, right? And I think don't have time really to tell you an example, but very much inspired by now large membranes of photosynthetic complexes. We have a couple of nice examples recently. So if you are interested, I can give you the exact references. So let me just finishing with some comments on what is really in the pipeline to move forward. So we expect that soon there will be the next generation of experiments involving both natural but also artificial complexes that have a degree of controllability. People are trying to develop at least theory. There's already quite a few papers trying to use entangled light sources to analyze what would be then the response of PBCs, including control that would be able to address specific regions in the two-dimensional spectroscopy. Recently, the group of Fleming has developed now mixed electronic vibrational spectroscopy to track simultaneously also the nuclear degrees of freedom. We have the aim to move beyond dimeric system and include in the full spectral density to be possibly able to determine to the response of FMO. And also from the very theoretical point of view, it would be nice also in trying to establish this relation between coherence and function to unambiguously characterize what are the sets of operations that can or cannot achieve a given task given some resources. There's been some work by Nicole Junger group and by us in the specific case of photoisomerization, right? And arguing what type of underlying evolution would be able to exhibit higher or smaller efficiency. Many people that contributed all over these years to the efforts in the group, I've just highlighted right, the people that are currently here, Martin and Jeremy, and you may know that Felipe tragically passed away in an accident in the Alps. So some review articles in case you are interested in going further. And also I've been very, very endogamic, mainly commenting on our results. There are of course many others by other people in order to construct what seems to be coming out, that this is this bibronical coherent PBC. Okay, many thanks for your attention. I hope I didn't overshoot too much. Thank you.
Thank you, Susanne. Now we have some time for questions. There is already one in the chat box. You can also read, but I can read it for you. This is about a porphyrin alignment and distance. is known to change energy level alignment without changing the color. There is a reference. And this question is there a structure-related effect in these protein complexes? That is how the iron oxidation is controlled at the porphyrin in hemoglobin.
Right. Okay. Take into account that here we don't really enter at this level of chemical detail, right? So for me, let's say, what is really, from the point of view of chemical groups, underpinning the behavior of the protein itself, right? So what is really, so this is the chromophore, and you talk about what may be happening with the residues of the protein in the vicinity, right? So for me, all that detail is encapsulated in the spectrum of the fluctuations. So what is, if you want, the microscopics behind that is something that at this level doesn't enter.
I hope this was an answer for our colleague. Okay, thanks, Boris.
Maybe just one comment for Boris.
Okay.
I think this comment actually emphasizes something, and is that to really make progress, right, we need a combination of studies, right? So let's say we can maybe shed light in some directions, right? But for instance, the type of question you put forward, right, that would come really from the physical chemistry community is also essential in being able to characterize in the more precise manner, right, what sort of description of the bad we can consider as realistic. So unless there is crosstalk in between communities, I think, especially in the long-reaching aim of making some relation to actual biology, will not happen.
Okay.
So there is a bit of talk, but definitely there should be more.
Okay.
Thanks for the question.
Actually, I have a question, Suzanne. This, with your experience in this vibronic coherence, what is your view about this explanation of lithium experiments, lithium isotope experiments? There was an initial claim about this role of spin, quantum origin, but there is also an alternative description where you can consider the different masses of the isotopes of lithium. Do you think that is it something related to vibronic coherence? Do you have?
To be honest, I don't know. This is something I've not studied, right? And I cannot tell you. It would be too risky to say anything. So okay. I don't know. Maybe, maybe not.
And something about this, what you call this noise assistant transport. Is there I mean, can you make an analogy with so-called resonant tunneling? You know, this was an interesting problem in the 80s after SIKSberg.
Yeah.
Is it something like opening a hole and then enhancing?
It really indeed belongs to the same category, right? Of having, let's say, the possibility of breaking coherent superpositions by means of incoherent effects, right? So in our case, if you think about forming the localized excitons that will not overlap with the reaction center, the situation of having dephasing and enhancing the transfer is very much like having a Mach center interferometer, right? Where you never, if it's perfectly balanced, right? For having no clicks in one of the detectors to include noise and now having clicks in both. So indeed, I would argue that it's not a surprise at all that the presence of noise will actually be favorable for transport. And indeed, there are many, many instances where it happens elsewhere. The issue is whether it's interesting that happens precisely in this type of complexes, right?
Yeah, I see.
Okay.
Thank you. There is one more question. I think we have some time for this from Barış again. If you want, you can read using simplest Guterman symmetry cascade argument. Each porphyrin is 4 oscillators in one, with each oscillator having a different dynamic correlation coefficient. Combining this with the flexibility of porphyrins, there is a rich chemistry. Did anyone
investigating this? I cannot tell you really. With this, you will have to really talk to the chemist. So, for instance, one person you could talk to is Elisabetta Collini in Padova. Elisabetta did very pioneering experiments with complex in algae, and she's a chemist by training, right? And definitely has tried to investigate microscopically the solvent interactions. And this would be a person I would target for this type of questions.
Okay, thank you very much. Is there a question?
Honor.
Yes. Can I ask my question?
Okay, please.
Zafer Hocam. I have a question regarding the utilization of resource theoretical approaches in this problem of photosynthesis. As far as I know, it's not too easy to generalize thermomajorization criteria in the cases where you have some coherences in the energy bases.
It's not easy what? Sorry, I didn't understand you.
As far as I know, it is not easy to generalize thermomajorization criteria if we have some coherences in the energy bases.
Okay, now you're talking about the case of employing resource theoretical.
Yes.
Yeah.
Yeah.
Okay, that I think it will be very incomprehensible for everybody in the audience if he has not read the papers. But what you are saying is absolutely right. That's why in this type of resource theoretic approaches, what you tell apart is certain type of operations cannot do. So let's say in our specific case, right, where we analyze the process of photoisomerization, what we consider are the abilities of operations that are not only thermal, but locally thermal, in order to be able to define in a consistent manner what would we mean by Markovian thermal operations. So if you ask me what happens if I remove, and there the conclusion is that non-Markovianity is able to enhance the performance, right? But there is a caveat, because you could be able to break the locality assumption. You could have operations that are globally thermal, but not locally thermal, right? That could be Markovian and maybe have a larger efficiency. And indeed, the reason I cannot solve that question right now is because I wouldn't know how to use thermomajorization if I break local thermality. So that's a very good question.
Thank you very much.
Would be nice to do. Yeah.
Thank you very much. Thanks. So thank you, Suzanne. We thank our speaker once again.
Thank you. Thanks a lot.
Thank you. So,
right.
By the way, hi, Francesco. Our next speaker is also from Germany. and also originally from another Mediterranean country, this time Italy.
Yes, exactly. Not far from Suzanne, yeah.
Yeah, so our invited speaker, Francesco Piazza from Max Planck Institute for the Physics of Complex Systems in Dresden. He will give us a talk entitled Quantum Nonlinear Optics with a Firm Surface.
Shall I share the?
I think you can.
Does it work? Yeah.
Yes, we see.
The pointer is visible. Yes.
Yeah.
Very good. Well, thanks a lot to you and all the organizers for putting this together, and Onur especially that they invited me and took care of all the questions I had. So it's really a pleasure to be here in front of this audience. And today I will talk about quantum nonlinear optics. That's the general framework, and in a new, let's say, in a new scenario, in a new setup where we hope could be stronger nonlinearities can be achieved. So, but this is a conference about quantum optics and information, so many of you are familiar with what I will say now, but let me introduce what is quantum nonlinear optics in a slide, like very quickly. So basically, in order to have, in general, nonlinear optics, we have to bring our photons to interact together. And of course, they don't do it at a fundamental level, so one has to use a medium where they can meet and interact with the interactions mediated by the medium. Now, in classical nonlinear optics, it is classical because typically, in order to have the medium affect the photons, you need to modify the medium a lot, which means that you have to put a lot of photons in order to have this back action. And this means that you have scattering not between single photons, but between what I call here photon lumps. So you have a certain lump of photon or two lumps that you have interact together, and they exit your medium in a correlated fashion. Now, quantum nonlinear optics means moving this scattering from a scattering between lumps to a scattering between single photons. So I have really single photons that enter the medium and correlate and exit again. Now, these interactions between single photons are very challenging to achieve in experiments, but these are, I will tell you, achieved in many experiments. And the trick is basically to increase the cross section for a photon to interact with the excitations of the medium. But if you manage to do this, then this is a very interesting technological resource, essentially, and most of all because the photons are ideally quantum information carriers. But so if you manage to have them interact, then you can do quantum information processing based on light. So that's of course. That's a very long-term interesting promise. And also you can do all sorts of devices based on single photons, like the full optical version of electronic devices like switches and so on and so forth. So many interesting technological prospects appear if you manage to implement quantum nonlinear optics. And basically quantum nonlinear optics is now quite established in various type of platforms, and most famously maybe is using atoms or artificial atoms in cavities, in optical cavities. Instead of using strong coupling mediated by cavities, you can use atoms with a strong dipole, which are Rydberg atoms, for instance, Rydberg states. Or you can confine light using evanescent waves, like in photonic crystals, and put atoms close together to generate these nonlinearities. So your medium is generically made of atoms or artificial atoms. But I would claim that basically these classes where quantum nonlinear optics is quite well established, in all these classes, the matter, the medium, is classically correlated. But there is a new set of experiments that is appearing, where the medium which you use to generate this quantum nonlinear optics is made of quantum correlated matter, and in particular fermionic matter. And there are recent experiments where you can have single photons strongly interacting with Landau levels in a semiconductors. You can have excitons, like hybridizing with photons, creating polaritons and then interacting via with a 2D electron gas in recent experiments at ETH, or you can have even single photons interacting potentially strongly with metals or superconductors that can be realized in solid state bulk materials, and also in more synthetic materials made of ultra-cold atom clouds. So all these new platforms that emerge, where basically you can hope to make single photons interact via the excitations of a quantum correlated material. And my question is then the natural one. Our question is, how does quantum nonlinear optics work if my material is quantum correlated, especially as fermionic correlations? And the model to study this, well, before I go to the model, I will say that today I will talk about a specific kind of quantum correlated material, which is simply a metal. So it has a Fermi surface due to the fermionic correlation, and it has Pauli exclusion principle. And let's ask the question about quantum nonlinear optics there. And this is a work done by a PhD in my group, Kieran Fraser, who is now finishing, and also postdoc Bernard Frank, that was at our institute and now moved to the Technical University of Dresden. So the model. The model, for those of you that know quantum nonlinear optics, well, you're typically used to study single photons interacting with the typical quantum emitter, which is a two-level system, right? But instead here, I want to have single photons interact with the motional degree of freedom of quantum degenerate particles. So here I write the second quantized Hamiltonian for some moving particles, can be electrons or can be ultra-cold atoms. Then this is the free part, the kinetic energy, the potential. Then I have my electromagnetic modes with a set of frequency omega mu. And then I have the light matter interaction, which takes this QED type coupling. So I have basically the density of my matter is coupled to a certain quadrature of my electromagnetic field in a quantized fashion, and I have a set of electromagnetic modes which I label with mode functions eta mu. Now, this is quite a general form, and how can this be realized? And this can be realized in two different, both in synthetic materials like in atomic gases, where you basically use two photon transitions, and you have basically a laser photon that excites off resonantly an internal atomic state, and then the de-excitation is made through a photon that, for instance, belongs to a cavity. And if you go to the dispersive regime for larger tuning, when you can eliminate the internal dynamics of the atoms, then you are left with the motional dynamics of your atoms, and generate this type of coupling here. A similar thing can be done also with electrons in solid state, also using two photon transitions in ways either driving off resonantly using the diamagnetic terms, or either for the excited bands. I don't want to enter this, but basically these are all ways of realizing this QED type coupling. So differently from the standard nonlinear optics, where you use internal degrees of freedom of atoms, here we use the motional degree of freedom of atoms or electrons. And since the motional degree of freedom can be brought by cooling to a degeneracy where the quantum statistics of the particles matter, then the quantum correlations become more and more important, and we shall see what are the effects on quantum nonlinear optics. So maybe before I go on, I should stop. Maybe if somebody is confused by the model, or I completely confuse somebody that this is very unusual for some people, maybe before I go on, I shall ask whether everybody, or not everybody, but at least most of the people are kind of okay with this model and understood the setting. So maybe I want to stop here. Not necessarily for long, but if somebody has a question.
I don't see any question in the chat box, at least. So
either it's great or it's a disaster. But so let me proceed. So the first thing, I see something in the chat, but it's probably not okay. So we want to use this medium of quantum correlated matter to study interactions between photons in this medium. Before we study interactions, we have to study how the photon is dressed by this medium, how the polarization effects work. And basically, this is I'm writing here for an homogeneous system of particles, how the polarizability due to this type of coupling I'm used will look like. And this is simply a density response function because my photon couples to the density. And basically, microscopically, the process is that a photon, this wiggle line comes in, removes a particle, let's say in my metal, you would remove it from the Fermi surface, from the Fermi sea, and put it out of the Fermi sea and generate the so-called particle Hall excitations. And then the photon leaves the medium again, and is re-emitted by the reabsorption of these particle Hall excitations. And this is the diagrammatic representation of this process, where you have the Hall line, the particle line, and the incoming and outgoing photon. And this polarizability is known is not an unknown function, and it has the usual behavior. It has a denominator, which is the vanishing at resonance, where the energy of the particle Hall excitation corresponds to the frequency of the photon. So this is what one expects. And then it has the balanced nk minus nk plus q, the balance between let's say in and out processes, basically. And this quantifies the fact that if I have both states occupied, from where I take and I move and I put my particle, this should not have any effect on the polarizability. And this tells you already something about the good regime where to have strong polarization effects, which is the regime of very cold matter, because hot matter has a very broad distribution in momentum. So these two nk and nk plus q by fixed q momentum of the photon will have some overlap if the matter is very thermally broadened, which will decrease the polarizability. If I instead manage to cool the matter and especially reach this quantum degenerate regime where I have either Bose-Einstein or Fermi-Dirac distribution, then this thermal broadening is minimized, and these two distribution functions don't overlap, and I kind of maximize my polarizability. So it's good to have cold matter. And but how this polarizability actually behave? So the polarizability, as I told you, is strongest at resonance, and the polarizability is a complex function. It has a real part which quantifies basically the change in the the change in the photon dispersion due to the dressing with the excitation of the medium, and it has an imaginary part that quantifies the absorption. So how much is it? The amount to which these processes which conserve energy and momentum lead to the fact that the photon can be absorbed by the medium. And if I take this metal, so I take a medium which has a Fermi surface, a sharp Fermi surface, and I confine it in 1D, which is a thing which you can do both in solid state and these ultra cold atoms. And I take this because it's the most striking regime for this new nonlinear optics. The polarization function looks like that. So for people that know polarization function of emitters, this is very different, and I will compare it later, just in a second. But let me say, first of all, you see that the absorption, which is the imaginary part of chi, it has a box structure. And in particular, you have these windows outside this box where there is no absorption. So, and this is strange, but this happens because my medium is quantum correlated, it's fermionic, it has Pauli blocking. So due to Pauli principle, you cannot have two fermions in the same state. So the photon cannot scatter, photon at a certain energy cannot scatter a fermion into an occupied state. This prevents on-shell processes and so prevents absorption. But still, what is very interesting, I can have still strong dispersion, a strong real part, even where the absorption is zero. Because here you see in 1D, I even have a logarithmic divergence of the real part, so of the polarization, of the modification of the photon dispersion, even though I have no absorption at all. This is very strange. Let's compare it with what you have with standard emitters. If you have a medium of emitters or dipoles, let me have to click. So then the polarizability looks rather like this. And this is when you have a strong when you want to have a strong polarization, a strong hybridization of the dispersion of photons with the material, you also have a quite appreciable absorption. And this is the problem you have to solve in general if you want to do nonlinear optics, quantum nonlinear optics. And in a medium of emitter, this is solved by the famous trick, which is called electromagnetically induced transparency. basically instead of using two-level system, you use three-level system, you dress them with a laser, and you can generate destructive interference between processes that would lead to absorption, and you can generate a window in frequency very narrow where the absorption goes to zero, and still you see the dispersion is still appreciable. It grows linearly across this zero, and this is the regime where you want to do quantum nonlinear optics with emitters. EIT is really the technique to use to do quantum nonlinear optics with emitters. And I would compare it to what we have in our fermionic quantum nonlinear optics with a Fermi surface, where instead of having a narrow window, which is actually a point, here we have a whole flat window where you have strong, let's say, dispersion and with exactly zero absorption. And so this is a kind of very interesting starting point to do quantum nonlinear optics. And this is really Pauli principle, is the quantum correlation of the medium that do that. So now we determine the polarizability. Now we can look at which kind of collective excitations emerge, the so-called polaritons, where my photons hybridize with the excitations in my medium. And this is the spectrum of this collective excitation, these polaritons. And you see this, you have these two sharp lines. This is a spectrum of the collective excitation. And you have these two sharp lines, which are these polaritons. And these are sharp because outside of this continuum here, which corresponds to this box here, outside of this, as I told you, you have basically no absorption at all. So you can have these very sharp resonances with which are by far not like photons, because their dispersion is very different from the photon dispersion, which will be this parabola here going up here. So this is very much not a photon, is strongly dressed by the medium, but is absolutely not experiencing absorption at low enough temperature. So this is very good thing. Now I can think to use this to excite these polaritons and have them interact without absorption and do quantum nonlinear optics. And so let me then compute now, imagining sending two photons into my material or into 1D metal and see how strongly they interact. For this, I have to compute another polarizability, which is what opticians call chi3, which is this nonlinearity here. And I can compute this chi3 is a function that depends on 3 frequency and 3 momenta. I'm plotting here this for specific values as a function of the like this is basically the difference between, this axis is the difference between the ingoing momenta, and this is on the x-axis is the transferred momentum in the scattering. And you see in this color plot, this is the strength of the real part. This is the strength of the actual good coherent nonlinearity that we would have. And you see there is a lot of structure, a lot of large values and small values. So it's good to take a cut. I take this cut here, and I show you as a function of this transferred momentum that this nonlinearity can be very strong, and they can have a lot of resonances, logarithmic, similar to the ones we saw in the polarizability, in the linear polarizability, and also algebraic here, even stronger. So really, we have the potential, due to these almost resonant particle Hall excitations that happen in this vertex here, to have really strong nonlinearities. But that's of course not the full story, because I have also to make sure that my third order, like chi3, doesn't generate further absorption, because this can happen as well. So let me then go to a more concrete, like experimental case, where I send 2 photons resonant with these polaritons here, at so now finite frequency, finite momentum, and I send them with opposite momenta. And now I look at both the imaginary part and the real part of this chi3. So the real part is what I showed you before, that has these strong resonances. And I see, again, due to Pauli principle, there are the windows also in chi3 where there is no absorption at all. So basically this box here, for instance, inside here I have no absorption, but still a very strong algebraic divergence in the coherent nonlinearity. So here, photons or polaritons can interact very strongly, still without experiencing any absorption, both from the linear and from the nonlinear polarizability. So I think that is the working point where one can think to study quantum nonlinear optics with very high, let's say, single photon nonlinearities and basically negligible absorption. So that is basically the main message of this talk. Let me complete this because, you know, if you study scattering between photons, you can study actually the scattering phase shift. And sometimes a good quantification of how you can do, for instance, a quantum gate between two photons is to study the scattering phase shift and the probability to have a pi phase shift without absorption. And here, basically, you see in this exact region, you can have these two, the scattering phase shift to be pi, exactly in this region where there is no absorption. So this again is a very good, and you can think about doing really a pi like a photon gate in using this metal in 1D at low temperatures. So this, of course, every idealized. We can have a discussion about how this is corrected, and I would be very, very interested in hearing opinions about what can be experimentally relevant correction to this. We have, of course, ideas about that. I'm happy to discuss them. And before I proceed, I want to ask how much time I have left, whether I can show a couple of slides more, or I can jump to the end.
We have time.
So do we have time for 2 more slides or so?
Sure.
Okay, so, well, because now I told you about single photons, a pair of photons interacting in this medium with strong nonlinearities. Now I want to show that actually there's another interesting nonlinear effect that you can have here, where even the formation of polaritons itself can become nonlinear. And this happens because, again, in this, due to the fact that you have the Fermi surface, as I showed you in this plot, there is this particle continuum that has this form in this is true in 1D, and you see that the particle continuum here touches 0 frequency. So actually, when my photon momentum Q is equal to 2 times the Fermi momentum, which is the size of the Fermi line, let's say, of this metal, then I have gapless excitations around at finite momentum, which is a simple thing. If you have a Fermi surface, a Fermi C here, and the photon has the right momentum, you can transfer a particle from one side to the other of the Fermi surface, which costs no energy, and still transfers a finite momentum. And this is known in solid state like the Pyrus instability, but basically it means that my system actually, if you couple it to photons which have momentum 2kF, or at least some of the photons have this momentum, my metal would become unstable and become an insulator and gap out the Fermi surface. So if the Fermi C is gapped out, so basically there is no more gapless excitations. And this is done by forming a spatial pattern in my material, which is dimerized. Basically, it has the right period to gap out the Fermi surface, and basically my system chooses one of 2 possible dimerizations. Basically, it gets this modulation by breaking a discrete symmetry, like which is inherent in the system. And now I want to study how the excitations in this dimerized phase work, in this dimerized insulator. And you have 2 types of excitations. You have the standard polariton, if you want, where you have a photon comes in and as an energy that can overcome the gap and excite again a particle excitation. So this is basically similar to what we analyzed before. So I just excite really a particle in its own lattice. But there is a lower energy excitations that a photon can induce, which is basically an excitation that involves also the deformation of this lattice. So basically, my system prefers to deform the lattice and create a bound state here, which is in the middle of the gap. And so the particle is excited into this bound state, which corresponds to this deformation of the lattice. So this is cost actually much less energy than the normal, let's say, polariton. And this is actually basically where the photon is interacting with instead of a simple particle excitation, is interacting with or hybridizing with a domain wall. And this is basically an intrinsically nonlinear type of polariton. And this is actually very interesting because it's basically a topological polariton. Because to remove this domain wall, you will need to globally change modify your lattice. So there's nothing local that can remove this. So this is very interesting because if I can store my photonic excitation in such a topological excitation, so I make my polariton and in principle the quantum information that I might store in my photon, that is contained in my photon, I can store it in a topologically protected excitation. So it would be interesting to investigate how this can be used for quantum information storage. And this is basically analog to the excitations that you have in these known SSH models for polyacetylene, for instance, where you have this dimerized patterns, and you can excite these solitons. But now, instead of having phonons, like in polyacetylene, we have photons here. And for quantum information, the photon is surely the better excitations with respect to the phonon. So as I said, this might be interesting for applications of this type. So with this, I should stop, and thanks for the attention, and hope for some questions. Thanks.
Thank you very much. Thanks, Francisco. Any questions? We have a question from Onur Umurcalılar. You can also read if you want. Is your model suitable to be coupled with schemes that produce artificial gauge fields, for example, to get to the fractional quantum Hall effect regime?
Yes, this is something which is actually on our list, because instead of coupling, I should go to basically our list of things, and there is this thing of coupled to other electronic phases like superconductor and magnets, and this is actually these experiments that I showed you in the beginning is actually Jerome Feist at ETH also, and this experiment here, basically, where they now I jump ahead. They basically, instead of having a photon exciting a metal, they have photon coupled to Landau levels. Basically, the photon is coupling to different, is driving the excitations between two different Landau levels. And in principle, this can be, Jerome Feist can study both the integer and the fractional quantum Hall, and you can study the corresponding polaritons like that are formed, and even quantum linear optics. And he has, even the interesting thing is that the coupling between matter and light in this Jerome Feist system using these split ring cavities are called in these monolayer materials. This is huge. Is in what is called the deep strong coupling regime, where the coupling is even larger than the characteristic photon frequency. So it's really huge coupling. So it's very promising. He studied already the effect of this on how the quantum Hall effect is modified by hybridizing with photons, and it's very interesting new direction.
So do you see the question from Sevilay Sevinçli? What is the order of magnitude of Chi3 comparing the other nonlinear medium?
Oh, this I don't know, because I have no numbers now in my mind. Compared to other nonlinear media, I cannot tell it on top of my mind. I should look into our calculation and look into other nonlinear media. But I think more than the actual absolute number, I think the quantification of how good your nonlinearity is to do, for instance, like a quantum gate between two photons, is to look at the phase shift. Because if I can do a pi phase shift without absorption robustly, then I have the necessary nonlinearity that I need, I think, at least for that. So I would, instead of quantifying how large Chi3 is, I would ask myself, what is the device that you want to build and which Chi3 do you need? But I agree with you that it would be interesting to put numbers and compare, and this I'm not able to do now, sorry.
Thanks. Let's move to Barış Malcıoğlu. Any suggestions for systems that can topologically protect these states? To be more specific, do you see any potential in 2D correlated materials that are quite popular nowadays?
Yes, we are studying. I mean, I mentioned now this quantum Hall bars coupled to strongly to single photons. And there are also at ETH, there is Atachi Momogu as, for instance, these transition metal dichalcogenides coupled to photons. And these are all interesting sources of quantum nonlinear optics. Actually, we are studying this also in this paper. I didn't have the time to mention. We are studying optical nonlinearities in transition metal dichalcogenides, so these 2D materials. And these are also interesting for generating not only nonlinear optics, but also coherent light sources of all sorts, because the excitons are really tightly bound. Regarding topology, the only topology we studied personally is this 1D SSH type of topological polaritons, but we just scratched the surface, because now we can study, as you mentioned, all sorts of 2D materials with topological band structure and see how they hybridize, how they address photons and with or without magnetic fields. And so I surely envision a lot of interesting things to look at. Yeah.
Okay, thank you. Two more questions, one from Levent, and then Emre Yüce will ask himself, I think. Levent Subaşı asks, can you comment on the relevant temperature scales?
Yes.
Is called referring to Fermi temperature.
Yes, that's absolutely relevant. Let me pick one slide, let's say this one here. So, because for instance, you will say, look at the optical nonlinearity, the real part, so the good coherent nonlinearity is large here, let's say here or here, and this box is perfect, so I have no absorption, but it's perfect only at t equals 0, like t much smaller than tf. So you should ask, how large can the temperature be in order for this effect to survive with respect to the Fermi temperature? And the thing is very robust, because this is, if you increase the temperature, this box is not that immediately becomes smeared out, but it has only a small exponential tail, which is basically decaying like T over TF. So basically, in cryogenics or in ultra-cold atoms as well, you can have really a temperature which is like 0.1 TF, and in solid state even much less. And so I think this is very robust with respect to temperature, because this is only an exponential correction, and so it's not that you get a large tail immediately. I think what is more relevant, especially in low dimension, is the robustness against interactions between your electrons or the particles, because if you add interactions to a metal in 1D, you get a Luttinger liquid. And these are has a completely different spectrum of excitation. They are not your normal particle excitations. And so we are studying this now, how robust it becomes if you add interactions. And so, yes, but that's the relevant question. And it's a good news with respect to temperature, for sure.
Thank you. So let's pass to Emre.
Thank you very much for the presentation. My question is about the relation between the real and imaginary parts of chi3. So we know that via Kramers-Kronig relations, they are related in linear regime, of course. So how about in chi3? Don't we expect such a relation also?
Of course, yeah. It's just more complicated, I would say, because the frequency dependence is more complicated. So, yeah, you're absolutely right. The Kramers-Kronig relation always exists because those are always retarded response function. And so they have the poles on only one side. And so you can always write a Kramers-Kronig relation. We didn't use it to compute it, but we compute them both separately. But we could have just computed the real part and then obtained the imaginary part from it, or vice versa. So I can tell you that the Kramers-Kronig relation are respected in our chi3 because we computed it correctly, otherwise it would be wrong. But I don't so, or are you asking, can I use the Kramers-Kronig relation?
Region, if you look at the in-box region,
yeah.
If one of them is constant, the imaginary part, whereas the real part is changing. So
yes,
this I wouldn't expect actually. That's why I'm raising my question.
Absolutely, because if you take a constant imaginary part, you use Kramers-Kronig, you get an algebraic divergence, and this is what at the edge of this box, and this is what we get. So this is really, you could have guessed by Kramers-Kronig. Yeah, this is I guess what we said. Here is more complicated. You have a lot of features, because if you zoom into the real part, it actually does a lot of things here. It has log divergences, it has algebraic divergences, and it all depends on how many resonant processes you can get into these lines here, like how many resonant particle excitation you can create. So it's a very rich structure, and it depends on 3 frequencies and 3 momenta. So the only thing where I can use Kramers-Kronig and quickly intuitively expect what it happens is basically these flat regions here. But maybe we should think more about it to understand. I mean, the log divergences are already more difficult to connect. But still maybe possible, yeah.
Yeah, I mean, I didn't do it for chi3. I mean, we know it for chi1, of course, but
yeah, we use it for chi1, for chi3. It exists, but it's less practical to use. I agree.
Okay, thank you very much for the presentation. Thanks.
Thank you for the question.
Okay.
May I ask a question?
Sure, Sergey.
Could we come to the pre-last slide? The next one, I guess.
This one?
No, next one, please.
Next one.
Yeah. Well, it was pre-last slide in which we were discussing this new type of soliton. Yeah, like that one.
Yes. Yeah.
So, as far as I understand, so that unusual shape is a result of topological structure, right? Of Fermi surface.
Basically, you have this dimerization, and you have to This
Yeah, my question is, can you do the opposite conclusion? For example, the observing the specific shape of such solitons, can you restore the feature of topological structure?
Can you repeat the question? I'm not sure I understand.
I ask if you observe some macroscopic properties of such solitons, spectrum or whatever, can you restore the topological features, topological properties of the Fermi surface? Can you make like an inverse problem?
So that if I can measure something that tells me that I have a topological well, I would say in experiments, these topological solitons, not in quantum optics, but in polyacetylene-like materials, have been demonstrated, if you want, experimentally, by actually measuring the fact that you have a transmission or you have excitations at a frequency which is actually half of the gap of your insulator. So they know the gap, but they go excited and they see there is the response at mid-gap. If there is spectral density there, then you start thinking, oh, then I have something as some kind of domain wall, which is then necessarily topological because it connects to different dimerizations. So this is how in experiment they measure it. So in using optics, it could be very easy because if it's already hybridized with your photons, then you do transmission, or you can do pump probe, and you see surely something which is excitable. You see spectral weight inside the gap of your. So this is a good signal. And also the experiments are in solid state in polyacetylene. They put extra particles and they see how they generate, because every particle, if you put an extra electron, it should be accommodated in these domain walls, and the more electrons you put, the more domain walls you can form. And so you can also see in solid state, they can also, I guess, some way image this as well. You have these arrays of tubes in 1D, and they can see how these domain walls interact across tubes. So they can do several things which can also be copied here, let's say. But I have not say this is very interesting because, for instance, I think that I don't know is that in optics you have this noise from, if you couple it to a cavity, you have noise from the loss of the cavity. And it would be interesting to see how robust these solitons are to this noise from the cavity, for instance, because if I hybridize them with photons, then I will because they can move like quasi-particles, but if there is noise, and typically if the strength of the noise is smaller than the gap, they should be robust, but the noise from the cavity is very non-local because the photons are very delocalized. So one should analyze this, and one should write equations to study this, some kind of Langevin equation for the motion of these solitons. This is also on our list, but the strength is limited. We can do a limited number of things.
Thank you so much.
Okay, thank you very much for this presentation and the answers.
I stopped sharing.
I think before closing this session, we have some announcements.
Okay, thanks, Hocam. I'll take from here. Thanks a lot, everyone, especially Francesco and Suzanne for very brilliant kickoff to our meeting. I have a couple of announcements regarding the next session and the poster sessions. Just let me share my screen. Okay. I'm really sorry. Why I cannot share my screen. I need to give permission to. Okay. Somehow I cannot share my screen, but maybe if Levent can share his screen. Program, yes. Okay, so all times are GMT +3 here, so we will have a break now, like 1 hour and 15-minute break at this point. During this break time, we can use the GatherTown link that we have sent you through the email. I mean, it's a really easy place to socialize with people. If you want to talk anything, if you want to catch up, you can use the GatherTown. during this time interval. And then from 1:30 to 3 p.m. Istanbul time, we have the poster and pre-recorded talks sessions in the Gather Town. They are already there. So if you would like to take your time and watch the videos and look at the posters, you can go there. But the official time interval for posters and pre-recorded talks, the discussions for the posters and pre-recorded talks are between 1:30 and 3 p.m. And after that, in the second session of this day, we will have Steve Campbell from University College Dublin, Ireland. After that, we will have Göktuğ Karpat from İzmir University of Economics, Izmir. And then after that, we will have Francesco Ciccarello from University of Palermo, Italy. So a couple of notes regarding the Gather Town. So you can just click on the link and then pick an avatar and put in your name and enter the Gather Town space. It's quite easy. And then after that, you will need to use your arrow keys to navigate around the Gather Town. There are instructions written on the ground, you will see, but your avatar will move, can be moved using your arrow keys. And then if you approach someone, your camera and microphone will open up, and then so you can talk to anyone that you approach. And also, if you would like to interact, so we have three rooms in the Gather Town. Two of them are dedicated to pre-recorded talks and the posters. So if you approach to a pre-recorded talk or a posters, you will see the names of the people who are presenting. So if you approach them and press X, you will see a notification to press X, by the way. If you press X, you will be able to see the poster or the pre-recorded talk in full screen. So if the poster and pre-recorded talk owners can go near their posters and pre-recorded talks, it would be easier for people to ask questions or have discussions in the Gather Town. So, I mean, if you have nothing better to do, we are expecting you to join us in the Gather Town space. And that's all the announcement that I would like to make at this point. Thanks a lot again to Francesco and Suzanne and Zafer Hoca for chairing the session, and to all of you. Hope to see you in Gather Town, and if not, hope to see you at 3 p.m. Istanbul time.
Hello, everyone.
Hello.
Merhaba. I hope everyone can hear me now. Without any echoes. Merhaba. I hope everyone can hear me now. I think it is. So my name is Levent Subaşı. I am one of the local organizers. So we will hopefully get started in less than 5 minutes. So in the afternoon session, we have 3 talks, and Özgür Çakır from Izmir Institute of Technology will be hosting this session. So Özgür, I think you are muted.
Oh yeah, now?
Now we can hear you.
Okay.
So please go ahead.
I think we have 3 minutes, right? No.
Yes. What I meant was take it away.
I think we just need to. I can't share my screen at the minute. I think I need to either be made a co-host or allow screen sharing.
Thanks, Steve, for reminding me. If there are any problems, I'm also the host of the Zoom meeting. So please let me know. In the morning session, I forgot to turn off the bell notifications for people entering and leaving the meeting. So that can be very disturbing. So if something like that happens, please stop and let me know. Oh, Steve, can you please check if you can share your screen now?
Yeah, let me just double check everything's fine. So you should see my desktop now.
Perfect.
And hopefully the first slide, yeah?
Yes, thanks.
Perfect, okay. I'll just...
Hi, can I also share mine?
Hey, ciao, Francesco.
Hi, Steve.
Hey.
How are you?
Yeah, good.
Good to see you.
Yeah, you too. Hopefully we'll see each other in person soon, like.
Hopefully.
So maybe Francesco can also share his screen.
Yes, I just enabled him.
You see it?
Yeah.
Everything okay?
Yeah.
Yes.
Looks great.
Cool. Stop share.
Hi, Francesco, by the way.
Oh, hi. Hi, Boris.
Hi. How are you?
Good. What about you?
Fine, thanks. I'm fine. So are you visiting Steve or Steve coming down to Palermo?
Nothing's planned yet. I'm just hoping to start actually seeing people again in person. Like.
Okay, fine. Then, okay, I guess I need to send you a plane ticket or something like that.
I didn't take a plane in the last 2 years.
Okay.
No, you.
Are you going to APS this year, Francesco?
Where is it? No, I don't know anything about that.
The March meeting this year is in Chicago. So.
APS, right. Are you going?
Yeah. I decided I have money in my grant to spend, so I booked flights yesterday. I'm like, screw it.
Chicago, nice city. So this year is gonna be full in person or
hybrid? I think.
Hybrid. I think last year was online, was it?
Yeah. The 2020 and 2021 was all fully online.
Now, during the first lockdown, it was in person, I guess. I think. 2020.
No, it was cancelled last minute.
I was cancelled last minute. Right. I know some people who got there and had to
yeah.
Okay. So maybe Özgür can take it away from here, and we may begin slowly. Okay.
Unless we want Gök to also check his that his presentation is working as well.
Should I try now?
Yes, please. Yeah, so I expect we will have a very smooth session from now on.
Is it okay? Can you see?
Yeah, that's great.
Okay, now I will stop.
Okay. Now I think Steve can share his screen now, I think.
Sure. Stop share. Play. Yeah.
Okay, so hello everyone. I'm Özgür Çakır from İzmir Institute of Technology. So I will be sharing this session. So our first speaker in this session is Dr. Steve Campbell from University College Dublin. The title of his talk is Quantum Speed Limit in Continuous Variable Systems. Okay, Steve, stage is yours, Steve.
Thanks very much, and yeah, thanks to the organizers for the invite. Google actually reminded me that it was almost 2 years ago to the day whenever I think I was last traveling somewhere, and I was in Istanbul. Like I was over visiting Özgür and Barış, so I'm kind of chomping at the bit to get back on some planes and get traveling again. So hopefully KOBİT-7 will be in person again. But anyway, yeah. So what I want to chat to you about today is a little bit of work that we finished up recently on something which is kind of like dear to my heart. I've been working on these quantum speed limits for the last couple of years. And it's a little bit of work that I did in collaboration with Pablo Poggi, who's over at the University of New Mexico, and my other long-term collaborator, Sebastian Defner, he's the guy who kind of got me interested in quantum speed limits in the first place back about 4 or 5 years ago. And really, where we started was just trying to sort of answer a kind of more basic formalism question, which was we wanted to kind of formulate quantum speed limits whenever we applied them to some sort of infinite dimensional system. So I'm a kind of very simple person. I like focusing on like basically two-level systems and harmonic oscillators. That's where I live. And for dealing with discrete systems, there's a good framework already for exploring these quantum speed limits. But things get a little bit muddier whenever you get to when you go to infinite dimensional systems, mostly because the most powerful frameworks we have for defining these notions of speed limits requires things that don't like living too much in infinite dimensional Hilbert spaces. So we first of all set out just to try and see, could we formalize something a little bit in this way? And the sort of knock-on effect was this really nice analysis of some subtleties to do with emergent classicality. And that's kind of what I'll try and kind of cover over the next sort of 20-25 minutes. I think one of the really nice things about what this work did was that it sort of took what is the current way in which we define speed limits. The most common machinery we use is a kind of geometric formalism. We look at distances and rates of change of distances. But if you look at the actual original motivations of where this quantum speed limit comes from, it's based on the uncertainty principles. And by looking at a particular class of continuous variable systems that the audience here surely know very well, like these Gaussian states, we were kind of able to get a little bit more of a thread kind of back between these two pictures. So with that kind of quick overview, let me sort of launch into, just for those in the audience who maybe haven't come across quantum speed limits or have only sort of touched on it, I give a quick sort of 5-minute crash course into where they come from. And this is kind of where I like to start all of my talks on quantum speed limits, kind of, going to quantum mechanics 101 that we imagine that, we all probably are very familiar with. And we go right back to Heisenberg. So Heisenberg gave us the uncertainty principles. And if you look back into his original papers, in his 27 paper, he essentially wrote down the two famous uncertainty relations. So we have that the product of the variances of position and momentum, he said, was bounded by roughly about h bar. And similarly, the energy time and the variances in energy and time are also, we have the energy time uncertainty principle, which again has this kind of roughly bounded by h bar. Now, this was a little bit hand-wavy, a little bit imprecise, but it captured a kind of fundamental essence of quantum mechanics, this idea that there's a sort of inherent fuzziness associated with the formalism. Now, position momentum was put on a rock-solid ground very soon after. And it was, if you look in, Robertson has this beautiful paper 2 years later, where he essentially said, okay, look, position momentum, we can understand this, because in the formalism quantum mechanics, we associate these guys with matrices, then this relationship purely arises from the non-commutativity between the two operators that we define the measurements on, that we define position momentum on. So this is something we're all very familiar with. And in fact, then the beauty of Robertson's formalism then means that you can understand the uncertainty principles for any two observables. I pick any measurable quantities, I have a Hermitian matrix I associate to it, and then from there, I automatically get an uncertainty principle for those observables. So this is rock solid and has a very good physical intuition. The issue comes whenever we try and apply the same picture to the energy-time uncertainty relation, because time is a tricky beast in quantum mechanics. So when we look at this uncertainty principle, fine, we have a Hermitian operator for the energy. That's our Hamiltonian. But there is no Hermitian operator associated to time. So how do you interpret the energy-time uncertainty relation? That was kind of a question that just sort of hung over the early days of quantum mechanics, really up until about the mid-40s. And it was really Mendelssohn and Tam who I think gave the first proper interpretation of the energy-time uncertainty principle. And they did it really starting from Robertson's formulation. But what they realized was that the naive picture of the energy time you might think is to do with how accurately can you know the energy of a system at a particular time. But that's, again, like, because there is no actual time operator, that's not really a proper interpretation. So what they did is they said, okay, well, let's take Robertson's formula, let's take the uncertainty principle. We take the Hamiltonian as one of the operators in the commutation relation, and we plug in the density matrix of the system for the other one. And then what you end up having there is essentially just your evolution equation. And then they crank a handle, they go through a couple of little mathematical steps. But what drops out then was that this energy-time uncertainty relation actually said something about the intrinsic timescales that the system wants to evolve over. So it somehow defines kind of how quickly it naturally wants to evolve according to its Hamiltonian. Now, what was very nice by doing this relationship and cranking this handle, they looked at kind of, I think, a natural kind of picture. They said, okay, well, what does it mean for connecting between two completely orthogonal states? Let's say two eigenstates of the system. So we have here something like a qubit. So going from some initial state, let's say, down to the orthogonal state. This relationship, whenever you reformulate it using or you look at it through the lens of what Mendelssohn and Tam did, gives you a minimal time that is bounded by the variance of the Hamiltonian. So I switch here from an E to a H to be a little bit more consistent in this normal notation. And this, I think, was remarkable. I mean, it gave a proper interpretation of the energy-time principle, and it also and it comes from the uncertainty relation. So it's still rooted in this fundamental relationship of quantum mechanics, but it gives us a proper way of understanding it. Now, this is essentially where things sat for a while, because no one was that particularly, I don't think people dug too much further into it. And it wasn't until maybe the advent of kind of quantum computation and quantum information in the late 90s, when Margolis and Levitin were looking at a similar question. They wanted to know, but they approached it from a different perspective. So rather than trying to get a proper interpretation of the energy-time relation, they were just interested in the more pragmatic question of how fast can a system evolve. If I want to do information processing, say with quantum systems, how quickly can I flip a quantum bit? And that's what they did with so they asked this, they plugged in the Schrödinger dynamics, and they just asked, how fast does that system evolve? What they ended up getting was a similar relationship, but instead of being based on the variance of the energy, it was based on the average, on the expectation value of the energy. Now, what I think this sort of tells you, and the main takeaway message here, I don't want to get into the intricacies of the different derivations, was that while on the one hand you can view the quantum speed limit as coming from this very fundamental relationship to do with the uncertainty principle, you can equally think about it in a more pragmatic sense and say, well, just how fast is my system evolving? And you don't have to invoke anything to do with the uncertainty relations, and you'll end up getting something along the lines of this Margulis-Levitin bound. What this essentially meant is that, you know, there's a few subtleties associated with this formalism. So this is kind of what we'll try and get to in the next sort of 20 minutes. But one thing that was kind of clear in all of this formulation, regardless of what way you approach the problem, was, you know, we had a H bar appearing here. And so the intuition, as it were, or the sort of common accepted wisdom was that this is inherently quantum mechanical, particularly because the original formulation came from the uncertainty principle. The rationale then was that there was no classical analog to it. So, and that is well motivated when you think about starting from the Robertson uncertainty relation picture, but it becomes a little bit trickier when you think about it, how Margulis and Levitin approached it, because they just looked at how fast the system was evolving and based it more on the sort of distinguishability between the systems, between your initial and target states. So with that picture, there's nothing inherently quantum mechanical about distances. So it was a surprising couple of years before people realized, well, actually, you could apply the same sort of formalism to more arbitrary systems. So what I mentioned is that whenever we look at these quantum speed limits, this vanishing, if we take a limit of vanishing h bar, then, well, one way in which this speed limit time can vanish is if the corresponding speed itself diverges. And I'll kind of interchangeably talk during the rest of the talk between what a diverging speed means in terms of or equivalently a vanishing speed limit time. But to get back to what I was saying, the original formulations of these speed limits kind of relied on the uncertainty principle, but most of the work that we've done since, like basically starting from Margulis-Levitin and then all of the different formulations of it, kind of culminated a little bit in very recent papers that essentially said, well, actually, whenever you take a more geometric picture, whenever you think about speed limits in terms of just a distance in, let's say, in Hilbert space, or a distance in whatever space you define your states, that really what it comes down to is there is a notion of distinguishability. And then there's nothing inherently quantum mechanical about distinguishability. You can perfectly well define this for classical systems, and that's exactly what these papers did. They took exactly the same formalism that we use quantum speed limits and said, actually, even for classical systems, there are precisely the same sorts of bounds. So they cranked the handle. They used a little bit of they looked at Langevin dynamics, but they used a lot of the same tools that we used for the formulations of quantum speed limits to define a bound for classical dynamics that looked very like our quantum speed limits. And it relied on something which was based on the distance measure in the numerator divided by something which related to the generator of the dynamics. So for our Hamiltonians, for our quantum systems, this generator, if it's unitary, is going to be the Hamiltonian, but there are more general formulations. Now, the fact that this demonstrated that, I mean, there's nothing intrinsically quantum mechanical about the quantum speed limit, then kind of this is where we kind of came in. So one can ask, well, like, how quantum is the quantum speed limit if I actually start from some sort of reasonably quantum systems and quantum dynamics? So what those two papers did were they used the techniques of quantum speed limits, but for classical dynamics. So we then were a little bit interested in, okay, well, what if we have an actual quantum system and quantum dynamics? What does it mean if that quantum speed limit vanishes? Quantum speed limit time vanishes, or equivalently, if that if the quantum speed diverges. So the framework that we were interested in looking at then, where we wanted to apply it to Gaussian states. So this is where what I said at the start. If you look at how all of these formulations of the quantum versions of quantum speed limits, the quantum speed limits are formulated on, they're mostly based on distance measures in Hilbert space, and it's mostly applied to discrete systems. There's not so much done for continuous variable systems, because that generator, like most of the bounds for quantum speed limits, are generally related to something to do with the intensity, like a norm or something like that, of the generator of the dynamics. And what you'll find is that, like for instance, in the Mandelstam formulation, you have the denominator is the variance of the energy. And it's perfectly possible to have a diverging variance if you have a continuous variable state. So things got a little bit trickier when you were dealing with these things. So what we asked was, well, can we reformulate things for Gaussian states? Now, Gaussian states are really nice because I imagine most people in the audience are more expert in this than I. But they're really nice because they kind of straddle the boundary between being very quantum states, but having lots of very nice classical kind of limits to them. So, I mean, if you're not familiar with Gaussian formalisms, I recommend basically these two references. So there's a sort of tutorial book basically by the guys in Milan, and Stefano also wrote this really nice sort of like crash course introduction to optics in phase space. The main thing that we just need to know is that if basically in phase space, if you look at a Gaussian state, it'll just be basically a blob in phase space. And if it's essentially this sort of just circular blob, it's basically like, it's very like a classical state. But you can enhance its kind of non-classicality by squeezing it in the different quadratures in the different directions. So if you take a squeeze state, this is a state that has like certain kind of classical-like fingerprints, but is still very much so quantum mechanical. And then you can just move it about in phase space. And these are essentially the properties that we'll be tweaking a little bit now to look at what happens what happens now in the formalism for quantum speed limits. So we're interested in, can we define, if we restrict to this particular class of continuous variable systems, can we develop a bit of a machinery for studying quantum speed limits here? And so then this is where I said Pablo basically came in and did all of the work on this. So rather than tackle the general question of can we define speed limits for arbitrary continuous variable systems, if you restrict to these Gaussian states, then you have a very nice machinery to play about with. So what we do is we apply the same geometric picture. What we say is that in order to define a speed limit, what we want to do is bound the rate of change of the system. And so for that, we just need to define a distance in some meaningful space. So we use a metric that's based on the state fidelity. So if we have two density matrices, I can define a metric in this form. Now, speed limits for discrete variable systems had already been derived using this picture. So we just took the same machinery and said, well, okay, what happens if instead of dealing with with density matrices, we do it for the Gaussian formalism? So to move to the Gaussian formalism, we take our density matrices and we write them instead in terms of the covariance matrix, which is a discrete for a single mode, it's a 2x2 matrix, and then a displacement vector. And these guys basically tell you how blob-like the guy is. That's what we get from the covariance matrix, and whereabouts in the phase space it is. That's what that displacement vector does. By doing this, by just working in this picture, it's very reasonably straightforward to take this expression in terms of density matrices and write it in terms of the covariance matrices. Now, we're not doing anything particularly advanced or particularly insightful here at this stage. We're just defining what the distance metric is in a slightly different formalism. But what is nice then is that we can then define what the speed is, what the quantum speed for these Gaussian dynamics are. So we crank the handle of the standard speed limit stuff, we calculate, and then this is the kind of key expression. I write it here just for completeness. You don't really need to worry too much about it. Just suffice to say that we can write down, if I have a Gaussian state and it's undergoing some Gaussian preserving dynamics that I'm going to define by the generator G, I can write down a closed expression for the speed using the framework, this whole framework of geometric speed limits.
Can I ask you a question?
Sure. Okay,
Gaussian preserving dynamics, is it always conducted by a linear interaction, or nonlinear interactions? Also, some nonlinear interactions also preserve Gaussian nullity of the.
For this, I'm not into. I can't say with absolute certainty because I'm not an expert in Gaussians. But I think it needs. I don't think you can have nonlinear interactions. Otherwise, I think that leads to non-Gaussianity. I would expect, but maybe don't quote me on that. I'm sure there's someone in the audience who will know for sure more. Okay.
Thank you very much.
Yeah. But I mean, so for what we do, we restrict though to just this very straightforward Gaussian. Just actually, the dynamics we look at is borderline trivial. What we were interested in is saying, well, okay, look, I have a framework for studying quantum speed limits for these Gaussian systems. Now, what does this now? And because I know that Gaussian systems kind of had this nice property that they kind of straddle that boundary between being very quantum in some instances and being quite classical in others, can we understand now what it means for these, what I would call bona fide quantum speed limits, because they're for quantum states evolving according to some Hamiltonian. What does it mean for that guy to vanish? Because what we saw from the earlier before, there was this H bar that appears in the Mandelstam formulation of speed limits. And the naive idea was, well, without H bar, then you would have just classical dynamics. That's why you would just have classicality. So that's why we wanted to try and understand, well, now what happens if the speed as defined using this formalism, if that guy diverges, you have a vanishing quantum speed limit time. What does that mean? And can we tie it to some notion of classicality in a more rigorous sense? And that's essentially what we did. We started then, so we took Gaussian dynamics and we said, fine, let's imagine it's some multi-mode state evolving just on the harmonic oscillator. This is like sort of very simple dynamics for the setting we have. And we asked the naive question of, okay, let's go and do the naive thing and say, well, what happens if just Planck's constant goes to 0? We take the naive classical limit. And for this dynamics, for just a Gaussian state, what we end up getting is this expression can simplify down to essentially two terms. Now, there's a little bit of a change in notation. This U and this V, they're basically the same thing. There's a little bit of rewriting that had to go on. But the important takeaway point is that there was two terms that appear in this notion of speed. One, which would basically disappear if the state wasn't squeezed. And what we wanted to do was, for the first example, stick to something that is kind of, in some sense, quasi-classical. That's quite close to a classical state. So we said, okay, let's imagine there's no squeezing. What we had then was that the second term was inversely proportional to H bar. And so now we could see, well, okay, what happens whenever we take the naive limit of H bar going to 0? So this naive classical limit, the speed actually does diverge. So you see a vanishing quantum speed limit time goes hand in hand with a vanishing of like some intrinsically quantum parameter. Now, this is all playing a little fast and loose with, taking the limit of H bar to 0 is a bit artificial, but it gave, I think, our initial kind of little bit of insight into what was actually happening. Remember, we'd formalized everything here using the kind of geometric framework, saying, okay, well, we're just defining a distance in the phase space and the rate of change of that distance. But what we have now, if you take this limit of H bar going to 0, what that actually means is that you're essentially reducing the uncertainty in all of the observables. So the little sketch that we did out here was, well, the limit of taking H bar to 0, if we look at the state in phase space, is the equivalent of taking a blob and making it a bit smaller. By doing that, we go from this picture where there's still some overlap for, let's say, as you evolve the state, to if the blob is smaller, by taking smaller limits of H bar, they become distinguishable quicker. And so we kind of see that there's a bit of a relationship again between this geometric picture and then the kind of original motivation of the speed limits being related to uncertainty. Now, I still think that this initial picture, a little artificial because we're taking this kind of naive classical limit. But I think the really nice and most insightful bit that we did was then saying, okay, well, what happens if we take these kind of quite quantum, these Gaussian states and we make them quite quantum. So we do some squeezing. So we take that same expression that we had and we then say, okay, imagine I have a squeeze state in my phase space. I look at the exact same dynamics, the exact same evolving state on the harmonic oscillator again. But what happens now if instead of having just a blob, that kind of almost classical state, I take the quantum, quite a quantum state, I squeeze it in some direction. What you find is that the speed here is then is related to how much the state is squeezed. And now, I think again we get this kind of this nice kind of connection between the two formula, or the two ways of defining these speeds. Because really, what's happening here? We have that by squeezing the state in phase space, so the direction of squeezing, the state becomes like highly delocalized in some sense in the other quadrature. So here we squeeze along this direction, it becomes highly elongated in this way. What then happens is that the distinguishability of that state then becomes very easy for that state to reach an almost completely distinguishable state. The more you squeeze it, the smaller you need to rotate the guy in order for it to be almost completely distinguishable from its initial state. And if it's infinitely squeezed, then just a tiny rotation would be enough to make it a completely distinguishable state. So what you have there is that you have a diverging speed associated with infinite squeezing. And now we can kind of rethink about think about this again in terms of this picture of uncertainties. Because what are we actually doing? We are increasing the uncertainty in one direction at the expense of reducing the uncertainty in the orthogonal direction. So what we actually have is that a diverging speed here is associated to a vanishing uncertainty, but just in a particular direction, in a particular quadrature. So our main kind of takeaway message from these two pictures was that actually, when we have a genuine quantum speed limit, so defined for a quantum dynamics that isn't going to trivially vanish, the quantum speed limit time isn't going to trivially go to zero, but we have some meaningful dynamics. Whenever that quantum speed limit time vanishes in this geometric formalism, it actually still goes hand in hand with a very particular notion of classicality. So what I mean is that in the naive picture where h bar, we took a limit of h bar going to zero, well, this just kind of corresponded to the vanishing uncertainty in all observables. But for these squeeze states, I think it was much more insightful. What it said is that actually vanishing quantum speed limits, we say it heralds classicality. It heralds a very precise notion of classicality, that you have classicality emerging in at least some subset of observables on the state. I think this was quite a nice picture, because I think it kind of connected a little bit this geometric formalism back with somehow the original motivation or the original framework of these speed limits, that they are, although are arrived at in a slightly different way, they're still very much so under the hood. It still relies on this sort of fundamental property, this notion of uncertainty. If you reduce the uncertainty even in one particular direction, then you will, you can calculate, you'll see that a diverging speed in that observable, or for that state, then corresponds to a sort of very particular notion of classicality. So in the last 2 minutes, I just mentioned just a little, I guess, corollary that kind of comes from this, is that we're kind of highlighting that classicality now kind of comes in a few different flavors. I mean, normally whenever you think of classicality, I think most people will think of like an open system dynamics, where I have, I have some system in contact with an environment, and that interaction leads to some, like, let's say you end up with some mixed state for the system. What we're essentially saying here is that this notion of classicality, where you have a classical mixture of states, that is a very different notion of classicality compared to what we're calling classical here, which is a vanishing uncertainty. And these are like sort of just two different views, but labeled by essentially the same thing. We did some calculations for our formalism if you look at actual open dynamics. So if we took our contiguous variable state and stuck it into, I think we looked at like Brownian motion or something, so stuck it into an environment. And what you'll find there is that mixture, I mean, what happens if I start taking mixtures of states? By its very definition, that reduces distinguishability. And so you'll find that you'll never have diverging speed limits times for this type of classicality that comes from the mixing of states, while from this other notion of classicality that we're discussing here, which is really at the level of vanishing uncertainty. And so you have classicality at least at the level of whatever observable the uncertainty is vanishing on. These are two kind of different but complementary ideas. I guess what we also, I wouldn't have had time to discuss anyway today, was that, you know, we mostly focused on the pictures I showed you were basically for like a single mode or for a couple of modes that we were looking at. You can also ask the question of, okay, well, there are other notions of classicality you could argue. I mean, the mixing due to an environment, the vanishing uncertainty I'm talking about here, but also the large n limit. We normally would associate large n with kind of some notion of emerging classicality there. What we actually found was, I mean, there was an earlier paper we worked on where we saw that, you know, when you have large n limits, there are certain instances where you'll have these kind of diverging speeds and vanishing speed limit times. And in fact, this picture that we had here could all be kind of recast for in the formalism that we looked at now. So the large n limit we found could kind of be reinterpreted a little bit in terms of this kind of vanishing uncertainty. So again, large n kind of goes hand in hand with a particular notion of classicality that we can, again, you can capture, I think, by looking at this notion of like a diverging quantum speed. So I think basically bang on about half an hour. So I'm going to wrap it up now just to say thanks again for listening. So if you're interested a little bit more in reading about it, so the formalism is all kind of discussed a lot more here in this paper that came out just at the very tail end of last year. So the formalism is there. I think, you know, there's some useful things we can do with just by having a formalism for studying quantum speed limits for continuous variable systems. But equally, I particularly like this idea of trying to sort of dig into these different notions of classicality. So I'll just thank my collaborators once more and all of you guys for listening, and happy to take a couple of questions if you have anything.
Thank you very much for this nice talk. So we can have the questions. Yeah.
Can I ask a question?
Yeah, sure.
Okay. Did I understand correctly? Just I want to check myself. When it is squeezed, the state is squeezed, there is no quantum speed limit, you say. So it goes to zero.
The speed limit time.
Sorry. Speed goes to infinity. So sorry.
Yeah.
But for a classical coherent state, it is finite.
Yes. So if it's just a blob, basically.
What kind of a speed does this correspond to in, for example, in doing an experiment, whatever it is? I mean.
So okay, so yeah, this is a good question, and it's one of the things that I've struggled a little bit with, not even with this formalism, but more generally, even in the discrete variable case, discrete variable cases, you can define these speed limits. Like how we approach them is from this geometric picture. So we define a distance measure based, like here we use the fidelity.
Exactly.
Any distance. Now, what do those distances physically correspond to in in an experiment? That is a tricky question that I don't think has really been addressed yet. But I think here you could probably view it as kind of like, imagine like a transport problem. If it really was just a blob, or let's say you have some state here and you want to move it. If you reduce the uncertainty of the, let's say if the coherence, if you were able to tighten it, then if you were just to uniformly reduce the uncertainty, which is this kind of picture where you're taking h bar to 0, then you could move it a smaller distance. You would have to move it a smaller distance in order for it to be completely distinguishable. So what you'll find is that if you were able to reduce that uncertainty to 0, then an infinitesimal distance would be enough for it to become completely distinguishable. And that's kind of why the speed limit time vanishes. It gets a little trickier to kind of get the same view if you have these squeeze states, but I would imagine it's kind of like just rotating it a little bit. But your question, I think, is a good, valid one. There's not so many experiments done yet, I think, on speed limits, but there were some recent ones. There's a really nice one done by a group in Bonn, I think, Andrea Alberti, I think, where they looked at this transport problem. And so I think there's maybe some insight in there.
But another question is related. Is it important in which direction the squeezing is, in Q or P, or the speed limit is the same without the direction?
No, again, this is a good point. So what we have here in the squeeze case is that the speed the speed diverges and the speed limit time vanishes essentially in the quadrature orthogonal to the squeezing. So It does depend. It is important in which direction you're doing the squeezing here. So I think Pablo fleshed out a little bit of this in the paper in the example. He has a couple of examples or a couple of things where, depending on sort of what question you're asking of the state, what direction the squeezing is, you'll see that there are sort of maximum and minimum values of the speed that can be associated to it.
Well, why I'm telling this, because Q usually is thought to be corresponding to the electric field, and P is usually corresponded to magnetic field. So that it is important that it is in the electric field direction.
Well, maybe it's just it's just how we've graphically represented this might be confusing a little bit. I think it just it depends on the direction which you. Like I said, it does depend on the direction you've done the squeezing though.
Okay. Thank you very much for this nice talk.
Okay. Thank you. So I have a question. Is this quantum speed limit concept applicable to quantum tunneling problem?
Good, very good point. In fact, there was I think 1 or 2 papers last year that tried to address it. Tried to see if whether or not you could use the speed limit times, I think, to kind of understand whether or not like a particle spends a finite amount of time inside the barrier or not. I think you have to look up a paper by Cavan Modi has a couple of papers on it. So I think the framework can be used. I mean, because for the transfer, like, because essentially what you have there is kind of like a transport problem. So going from point A to point B. But if you have the barrier in the way, I think you can still use the same machinery in order to calculate it. And what I imagine is if the speed limit time will probably will be dependent on how intense the barrier between the guys is. I imagine some people must have looked at it at this point, but I don't know offhand.
Okay. Thank you very much. Okay.
So can I ask a question, or is it too late?
Okay, please go ahead.
Yeah. So, well, hi, Steve. Long time no see.
Hey, man.
So everything here was for like unitary dynamics, and I was wondering if I've understood the idea properly. Do you consider the effects of like measurements for quantum speed limits? Because then you kind of project instantaneously, or maybe it tells you something physical that the measurement has to take a certain amount of time, or do you ever go into that, or?
This is a very tricky question. So yeah, I mean, what we looked at was for unitary dynamics, and then we in the paper we do a little bit on these open system dynamics for like Brownian motion. But the subtlety of what happens for measurements, I think Adolfo Del Campo has a paper about trajectory based pictures for speed limits, and what you'll find there is that depending on how you unravel your dynamics, and if it's a master equation, then you'll have like sort of speed limits that kind of bounce all over the place, but the average value will be what the sort of standard formalism gives you. But the actual, let's say, what happens, like how fast does a measurement occur, that's not something I think that we've been able to address yet. But I guess that's kind of the trickiness associated to measurements in general. I don't know how much speed limits can help us with that picture, but people are maybe thinking about it a little bit, but we haven't done too much there.
Yeah, it's kind of a natural question. Okay, yeah. Cool. Thanks so much.
Cheers.
Thank you very much, Steve.
Thank you, guys.
Okay. So we can have the nice next talk by Göktuğ.
Okay, so I will share my screen.
Okay, please.
Can you see it?
Yeah, you can make it full screen. Okay.
Okay, now I can start, I guess, right?
Yeah, okay, so our speaker is Göktuğ Karpat, Dr. Göktuğ Karpat from İzmir Economy University. And title of his talk is Synchronization and Non-Markovianity in Open Quantum Systems. Okay, please go ahead.
Okay. Thank you very much for the opportunity to present our work on the relation between synchronization and non-Markovianity in open quantum systems. Let me start by giving a very simple definition of synchronization. Well, we said that synchronization occurs between two or more systems that are independently evolving in time, start to evolve in unison or in coordination in time. In fact, this is a very old concept. It was first recognized by Huygens as an odd kind of sympathy between two pendulum clocks, which are coupled via a support. It's indeed, the synchronization is indeed a widespread phenomenon that we can observe in nature. Indeed, it's everywhere. I mean, I will just show some examples. For instance, I'm pretty sure everyone saw the example of a bunch of metronomes being coupled, you know, when they're being synchronized when they're coupled through a common support. Or in the second picture here, you see a conductor imposing his own rhythm on the orchestra. These are different types of synchronizations, but, well, let's clarify that as well. There are two different kinds of, I mean, we distinguish typically between two different kinds of synchronization. The first one being the spontaneous kind. So we say that the spontaneous synchronization occurs just due to the coupling between the subsystems in the absence of an external drive. So in the short clip here, you see fireflies flashing at the same time, more or less at the same time. They're synchronized. I think this is for mating purposes or something. There is no external drive, so this is an example of spontaneous synchronization. The second type is known as the forced synchronization, and it occurs when the system is actually driven by an external agent who, acting as a pacemaker and who imposes its own rhythm on the system. Here you see this guy who is actually imposing a rhythm on the other people who are rowing. Also, if you remember the conductor imposing his own rhythm on the orchestra, this is another example of forced synchronization. But in this talk, I'm just going to talk about spontaneous synchronization, actually. Okay, so, sorry. The synchronization phenomenon has been studied, I mean, like relatively well in the classical domain, but in the last 10 years, we started to talk about quantum synchronization. So I want to clarify first what we mean by quantum synchronization. We say that usually, I mean, two quantum systems are synchronized when the local, I mean, the expectation values of the local observables of these two systems start to behave in a synchronous manner while they're undergoing open system dynamics as they are, evolving through the steady state. So it is a very simple example. Assume that you have two spin-half objects labeled by S1 and S2. You can turn on an interaction between them as well, but the important point is that they are interacting with an external environment. Okay, so what we're looking at, what we should look at here to check whether the synchronization occurs or not is the expectation, the dynamics of the expectation values of the local observables. For concreteness, you can choose, for instance, the spin observable along the x direction, sigma x, S1 and S2. And well, what you want to do is you want to check whether, I mean, after a trend, I mean, of course, you assume some detuning between them initially so that the problem is not trivial. What you want to do is to check whether after a transient, I mean, period of incoherent oscillations, whether they become synchronized, anti-synchronized, or, frequency locked in some way. In the last 10 years, it was shown that both pairs of spins and oscillators show this environment-induced quantum synchronization behavior. It's a, I mean, rather timely subject, let's say. It was just, I mean, people started to study this like a decade ago, and there are not many works on it. Still, there are a lot of open questions. So this is one of the first works which introduced this concept. So for, just to give a physical model, I want to say a few things about this. Here, let's once again consider we have two spin-half objects, and they are coupled to a common environment through some interaction Hamiltonian, okay? And these spins have different characteristic frequencies, omega-1 and omega-2, so that there's initially, there is some detuning between them, because if there was no detuning, the problem would be trivial, right? So it was shown that the synchronization can occur between the local spin observables, sigma x here, once again. But at this point, I think I should say that synchronization does not depend actually on the choice of the observable. For concreteness, we choose some observable and display the plots. But I mean, for any spin observable, this should work, okay? So it's a characteristic of the dynamics, not the initial state, not the choice of the observable. Okay, in this model, they choose sigma x just to show the results. And as you can see here, the initial evolution in the green inset of these two expectation values show that there's no sign of synchronization here. They oscillate these expectation values. And then after some, between 0 and 20, let's say, time, and after some period, there's a transient incoherent evolution. And finally, after some time, we can see that the anti-synchronization is achieved, and it is like it remains as the system evolves, to its steady state and so on. So this is just one. This was one example. Of course, there are like several more examples for oscillators and spins. I just wanted to show you so that you have a feeling, about what we are talking about. But now let me start introducing our model and our results. So in our work, we considered a collision model for several reasons. But I mean, it's not important at this stage, but they are flexible. One of the reasons that we choose collision models is the fact that they're flexible. You can engineer any type of environment you like. This is one of the reasons. But what we do is that we study the establishment of synchronization between the local spin observables. Once again, the system, the principal system, which consists of two spins, S1 and S2, experiences open system dynamics as described by a two-qubit collision model. There is no external drive or anything, so this will be an example of spontaneous synchronization. So let me, summarize the collision model, just the one step. So of course we are iterating this many times to reach the steady state of the problem. But in the first step, what we do is that we let the principal spin particles S1, principal system spin particles S1 and S2 interact directly with an XX type Heisenberg Hamiltonian. Here lambda is the interaction strength. In the second step, only S2 interacts with the first environment spin En with the same type of an Hamiltonian. In the third step, the S1 and S2, the principal spins, evolve with their free Hamiltonians, and at the same time, the environment spin En, which previously interacted with the spin S2, now interacts with the upcoming environment spin En plus 1. And in the final step 4, we trace out En and we continue with the same scheme with many, many more iterations. Here, maybe I should say that there are 2 points I want to clarify. The interaction between the environmental spins is described by a partial swap operator whose strength is characterized by this parameter gamma. So there are 2 parameters that are important for us: lambda, which is the spin-spin interaction, and gamma, which controls the strength of the intra-environment interactions. And as you can see, the first spin, S1 here, is like in some sense the probe spin here. It's not directly interacting with the environment, but I mean, it exchanges information with the environment over the spin S2, which actually directly interacts with it. Okay, so as you know, I mean, like you can guess from the title, I want to talk about the synchronization, the relation of synchronization and non-Markovianity. So I want to specify the measures because I want to talk about, this relation in a quantitative way. So I need to introduce the measures, right, for quantifying synchronization and non-Markovianity. First of all, to quantify the degree of synchronization between the spin observables, we use a standard tool from statistics known as the Pearson coefficient. And this coefficient basically measures the association between the discrete variables x and y. And in our problem, these parameters, these discrete parameters, will be the expectation values of the local spin observables, sigma x S1 and sigma x S2. Once again, just to remind you, you can choose any other observable. Unless you choose something really pathological, you'll get the same result. Okay, so how do we calculate this Pearson coefficient? For two given data sets, if you calculate this, you get a number. But we want to see the evolution of this number, which gives us information about, you know, the nature of synchronization. If Pearson coefficient goes to 1 in time, then it means that you have complete synchronization. If it goes to -1, it means you have complete anti-synchronization, for instance. So to be able to, you know, look at its evolution, we do the following. Well, we first run the simulations and calculate the spin expectations after each step of the collision model, and then we group these, we divide this whole data set into smaller data sets, like in this example, data sets of 5 variables. We also allow some overlaps so that our plots will be like smoother. This is just for cosmetic reasons indeed. And then we calculate for each sub-data set the value of the Pearson coefficient, and we draw it as a function of the collision number. In other words, we could say it's time. Okay, so you see, I mean, we check either it goes to 1 or -1 or 0, I don't know, some other number. This will tell us about the nature of the synchronization. Okay, this is how we quantify synchronization, but what about the quantification of non-Markovianity? Well, this is rather straightforward. I will not spend a lot of time on this because this is now very well known. We quantify memory effects using the well-known trace distance measure. So we check the dynamics of the trace distance, taking, you know, arbitrary initial states. And then if there is a temporary increase throughout the dynamics in trace distance, we sum these increases. And since the increase of trace distance can be, you know, interpreted as a backflow of information, we assume that this quantifies memory effects or non-Markovianity. Optimization and the definition of the measure here for the collision model can be done numerically, obviously. But I mean, I should also emphasize at this point that our results are, do not depend on the choice of the non-Markovianity measure, because we have considered in our work also other measures such as, you know, correlation-based measures like entanglement, mutual information-based measures, and we pretty much get the same qualitative results. Okay, but another thing that I want to emphasize is we are just studying I mentioned that the first qubit is the probe qubit, which does not directly interact with the environment. So we are just calculating and considering the non-Markovianity of the probe qubit here. So this is the one that we will be comparing with the synchronization measure. Okay, so here is our main result, I would say. Let me try to explain this. In the upper 3 figures, you see as synchronization diagrams. They're color-coded. C12 is the Pearson coefficient, 1 and blue, correspondingly. Blue means full synchronization is achieved. Of course, this is the value of the Pearson coefficient after, say, like 10,000 iterations, so that the system reaches its steady state. And you see the blue means full synchronization, and the red means complete anti-synchronization between spin observables. And in the upper 3 figures, you see for the same parameter set, the non-Markovianity diagrams, color-coded again. The black means 0 non-Markovianity, and the yellow means the maximum amount of non-Markovianity. This is normalized. Okay, so let's first have, vertical axis is detuning, or the ratio of the characteristic frequencies of the principal spins, and the horizontal axis, lambda, if you remember, quantifies the strength of the direct interaction between the spins, S1 and S2. If you have a look at the first 2 plots, the upper first and the lower first, you see gamma is set to 0. Gamma controls the strength of intra-environment interactions. Okay, this means that gamma 0 means that there is no intra-environmental interactions, so that the non-Markovianity, the only contribution to the memory effects, comes from the direct interaction between the spin S1 and S2, because we're talking about the non-Markovianity of the dynamics of the first spin. So this is the simplest case. If you check this, you see that there's a line which sharply separates regions of synchronization and anti-synchronization. And along this line, synchronization cannot be achieved. Okay, and now for the same parameter set, if you have a look at the non-Markovianity diagram, you see that the greatest degree of non-Markovianity is achieved along the same line. So this was the first hint that told us maybe there's a trade-off relation between the onset of synchronization and the degree of memory effects. But of course, this is the simplest case. So to make this problem more involved, we next turn on the intra-environment interactions, like increasing the strength of gamma further and further. What you see here in the synchronization diagrams is that this line, this asynchronization line, let's say, shifts in the upward direction, but exactly the same behavior is, happening. You can observe the same behavior happening for the non-Markovianity plots. So our conclusion was there is indeed really a trade-off relation between the onset of synchronization and the degree of memory effects in the dynamics. So in other words, memory effects hinders the establishment of synchronization. I know that I don't have a lot of time left. I want to show you just last two plots. This is for the same data set, but maybe it's easier to see the trade-off from this plot. Now, along the vertical axis, we have detuning, and along the horizontal, we have the intra-environment interaction strength, which controls the degree of memory effects coming from the environment. You see again this white line, along which the synchronization cannot be established. And for the same parameter set, now if you check the non-Markovianity diagram, you see that the maximal value of non-Markovianity exactly corresponds to the same line. So indeed, there's a trade-off relation. But one might wonder, there is in this region, for instance, there is non-zero non-Markovianity, but synchronization or anti-synchronization is still established. Yes, it's true, but the next plot explains what happens there. Indeed, as the strength of the non-Markovianity increases, the establishment of synchronization is delayed. It occurs at a later time. So for instance, if you compare figures A and B, A is for piercing coefficient, so for synchronization, B quantifies the memory effects. You see, these are, for different detunings. For instance, for the red line, we have the lowest amount of non-Markovianity, and the black corresponds to the highest amount. And in the synchronization plot, you see the black line reaches the value 1, the full synchronization, the last. So if there is more non-Markovianity in the dynamics, then the synchronization is reached, it becomes harder and harder to obtain the synchronized dynamics, let's say. So there's an inverse relation between two. Or to summarize everything, we can say, as the non-Markovianity increases in the dynamics, the establishment of synchronization is delayed further and further. And in some spatial region, it's so delayed that the synchronization can never happen. This corresponds to this white line here, followed by, this maximal non-Markovianity curve. Okay, so I think I'm almost out of time. So I will conclude by showing you the reference. And also, I want to say a few more things. Of course, due to the time constraint, I could not show all the results that we have in this paper. If you study the collision model, the results are numerical because you're doing numerical simulations, but we have also studied, master equation models in some simpler cases, because, with the collision model, you can do anything you like, but if you use the master equations, if you want to obtain analytical results, you're more restricted. But at least in some particular cases, we were able to show that this relation can be, shown to exist with analytical arguments. So if you are interested in the synchronization problem in the quantum domain, please feel free to also have a look at these two references, which are about the relation of quantum synchronization and quantum correlations and so on. Thank you very much for listening.
Thank you very much, Victor, for this nice talk. So I think Francesco has a question. Please go ahead, Francesco.
Yes. Hi. I just had a small little curiosity. You stressed at some point that your results are independent on the non-Markov measure that you choose, and you mentioned quite a few of those. These are actually all measures that depend on the open dynamics of the system.
Yes.
But you know that Campbell and others propose these measures, which also depends on the bath dynamics. So I was curious to hear if something changes in these conclusions.
No, I understand. Okay, well, maybe I should correct. We just checked, correlation-based measures and the trace distance measure. So I cannot, of course, claim that we have this. We have the same trade-off for all the measures. That's something that I cannot claim, obviously.
And also, I wanted to ask you. You've been playing, so to speak, with the collision models. I also play with that.
Yeah.
A lot. Are these? You think these conclusions are model independent, or so?
Well,
in fact, if you go for more sophisticated models, you find similar.
That is not guaranteed, of course, but we have played with some master equations, of course, under some approximations, right? Like some in the Lindblad form. Also, in the weak coupling with the collision models, we assume strong coupling. The results were the same, but of course, once again, I cannot claim if I complicate the model even more, which is easy to do with the collision models. I cannot guarantee that the same relation will be there, but it's not like a very specific instance. It's I don't know, like reasonably general, let's say.
Right. Thank you.
You're welcome.
Thank you. Any other questions? So go to what's the maximum dimension of the environment that you work on?
Here we are. This is a collision model, so we are just using spin half part qubits to model the environment, like many qubits. But obviously, since this is a collision model, they are traced out after each iteration. So you have two-level systems interacting with two-level systems, but after each iteration, you trace out the environmental system. So as you're doing the calculations, the full size of the system is never really very large. It's easy to do, numerically.
Okay.
I have a question. Can I ask?
Yeah.
Okay.
Please, go ahead.
You use the term non-Markovanity and the memory interchangeably, I think. Is it correct?
Well, it depends on how you define non-Markovianity and memory. It's correct to a certain degree. Well, what do you mean by it depends on what you mean by non-Markovianity. If you mean CP divisibility, and it's not equivalent to the BLP measure or correlation-based measures, but
my question is not this one, because if it is true, when you say the memory, you mean the memory shared by these two principal systems, or the memory between the systems and the environment?
I mean the memory. Okay. So non-Markovianity can come from two contributions here. First, since we are just talking about non-Markovianity of the dynamics of the first spin, it can come from the direct interaction with the second spin. Even if the two spin dynamics is Markovian, there will be non-Markovianity in the single spin dynamics. Or it can also come from the environment if you allow the intra-environment interactions in the collision mode.
Okay. But intuitively, I expect proportional between the synchronization and the memory, because if there is a memory share between these two systems, then I expect a synchronization between their evolution.
I'm sorry, I couldn't understand the last part.
I said, if this memory, or let's say, this memory is shared between the systems, then
Yes.
I expect a synchronization between the evolution of these two systems, because there is a connection between the two systems by means of this memory. Then, I mean, if there is a memory shared between these two systems, then I expect they behave very synchronized.
No, not understand, not like that. I mean, the second spin is still interacting with the environment, and it's undergoing decoherence. So the direct interaction does not guarantee synchronization. So without dissipation, there is no quantum synchronization. There must be dissipation. Okay, so although you have this direct interaction between spin 1 and spin 2, you must have some dissipation, because it's the key mechanism which enables the onset of synchronization.
Okay, thank you very much.
No problem.
Okay, thank you very much, Dr. for this nice talk.
You're welcome.
So we can have the next speaker, Francesco.
Yes.
So can you share the screen, please? Okay.
Do you see it? Can you see it?
Yeah. So our next talk is by Dr. Francesco Ciccarello from University of Palermo. The title of the talk is Quantum Optics in Topological and Non-Hermitian Photonic Cells. Okay, stage is yours.
Yeah, thanks a lot. I have 20 minutes, right? Okay, so thank you very much for the introduction. It's a pleasure participating in this conference, even though from my office. I wish I can participate in person maybe next year. Okay, so this talk is probably about something else compared to what you heard so far in this conference, and it's a little bit about overlap between quantum optics and other fields such as condensed matter. So let me start from what we know from traditional quantum optics. We know that compared to free space, if you place an atom in a cavity, then this may affect its interaction with the field in a substantial way. You can, for instance, think of a partial effect in a weak coupling regime, or in the strong coupling regime, you can think of vacuum-Rabi oscillations. So the take-home message is that if you change the electromagnetic bath in which your atom is immersed in, then this can modify its emission properties or even create interesting dress states, such as dress states occurring in the familiar James-Cummings model. Now, over the last few years, say about the last decade, thanks to a number of technological developments in field, in scenarios such as circuit QED or cold atoms, we can now fabricate relatively sophisticated photonic baths, and in particular photonic lattices, and study their interactions with atoms. So, for instance, you can obtain this by assembling coupled cavities or resonators, where each cavity or resonator can be locally coupled to a real or artificial atom, or generally, I should say, a quantum emitter, such as a superconducting qubit. Now, given that this is a lattice, even before its coupling to the atoms, the field normal frequencies will be organized generally in bands and generally separated by band gaps. So assume now to make an atom interact with your photonic lattice and say that the atom frequency is set well within the band gap. You see that in general, a dressed bound state, and this is a dressed atom photon bound state, will arise at a frequency near the original atomic frequency omega 0. And in this state, the atom is dressed by a single photon exponentially localized around it. Now, a major appeal of these bound states in this literature is that you can exploit them in order to mediate effective Hamiltonians, namely effective interactions between the atoms, which can be even decoherence-free. And you can think of two nearby atoms. Each atom forms its own addressed atom photon bound state. When you start making the atoms approach one another, the photonic wave function of the respective Mount state will start overlapping a little bit, and then similarly to the formation of a molecule, you'll get an effective atom-atom Hamiltonian, and due to the fact that everything here happens inside the photonic band gap, this is actually decoherence-free, and this is quite exciting because this way you can engineer sophisticated many-body spin Hamiltonians and all the related applications, you know, for quantum technologies and quantum simulations. Okay, so what's next now? What's the situations today? This is the current perspective. So if you broaden your viewpoint a little bit and think of fields such as condensed matter, nanophotonics, and even beyond, we have in particular two big actors, so to speak, on stage. One actor is topological phases, another actor is non-emission physics. And you can see that these fields are really exploding, in particular non-emission physics in the literature, and there are interesting connections, many connections between the two. Now, the natural question is, what about interfacing, combining these things with quantum optics? Is there any interesting chemical reaction that can arise by mixing these concepts? And this is a question that people started asking recently. Okay, so let me start from topology first. It's a kind of milestone of topological theory of topological phases in condensed matter that if you're given a translational invariant lattice, such as the one sketched here, and this features bands and band gaps. Now, and this lattice is a non-trivial topological phase, then if you break translational invariants, for instance, through a defect, which can be a vacancy, as for instance, in this case, but not necessarily a vacancy, it could be an impurity, it could be just an edge of your lattice and so on. Then you will see appearance of so-called edge states, which are localized localized stationary states, which are topologically robust and which are energetically lying right at the middle of the band gap. Now, what about importing these concepts into the quantum optics domain? Can we do anything interesting with that? So in this case, we should, instead of a lattice, which is normally thought in the condensed matter community is a lattice of electrons, we would have a photonic lattice, and this photonic lattice is now made to interact with one or more atoms. Can we do anything interesting with that? Okay, so one rather natural thing that we can do, and this was done both theoretically and experimentally, is that we can exploit these edge states, not only for one-dimensional system as the one that I sketched before, but also two-dimensional systems. We can use this edge state as a bus, for instance, to accomplish quantum state transfer between two atoms, or in the case of two-dimensional systems, we can use edge states in order to engineer chiral emission from one emitter. These are kind of rather natural application in the sense that what you do in these cases is that you have your lattice under open boundary condition. The lattice already before coupling to the atoms exhibits these edge states, and now you couple the atoms, use edge states as bus. But now a more interesting question can be asked, which is the following. What if I have my photonic lattice and I go for one, I'm admitting a topological phase. This is translationally invariant. And now I couple it to an atom, and it's decoupling to the atom itself that breaks translational invariance. What happens? Shall I predict and observe occurrence of edge state? But if so, this would be dressed edge state. What does happen? You see that this is like specializing the problem from a defect, static defect, to a defect featuring quantum internal degrees of freedom, or quantum defect in short. So the first time people answered this question was about 2 years ago in this paper, and they considered a specific model, which is the celebrated so-called SSH model, the photonic version actually of the SSH model. This was a theoretical answer, but which was experimentally confirmed last year in a circuit QED architecture in the Oscar Painter's group at Caltech. What happens is that indeed, if you tune the atom's frequency right at the middle of the band gap, in this case you have only 2 bands, then a topologically protected dress state whose wave function looks quite like that you would get in the case of a static defect arises right in the middle of the band gap. And you can exploit this topologically protected dress state in order to engineer effective atom-atom Hamiltonians according to the framework that I sketched before. And these have interesting dependencies on the atom's locations and distances. So far, so good. And but now there is a natural question that you can ask, and this is what we asked last year. All of that was proven for a specific model, the SSH model, which is actually, as far as I know, the simplest lattice model exhibiting topological phases. But the question is, what about the general model? What are the general criteria for occurrence of this topologically protected dress state? And if so, what are the general properties? Now, in order to reply these questions, we exploited clues from the SSH model. One clue is that if you look at what I said before, namely that you have appearance of this dress state and look at the photonic wave function, the photonic wave function shape is just the same shape that you will have if instead of breaking translational invariant through an atom, you will break it through a vacancy, namely you introduce a vacancy in your lattice without any atoms. Second, and even more interesting clue is that it turns, as I said, if you tune the atom frequency right in the middle of a band gap, then a dressed topologically protected edge state will appear again at the middle of the band gap, and this is just the same frequency as the atom. Now, remarkably, this takes place regardless of the atom-photon coupling strength. So regardless of the atom-photon coupling strength, you'll get the dress state occurring just at the same frequency. Its shape, namely its wave function, will be affected by the coupling strength, but it will always be pinned to the energy, same energy as the atom. This is kind of counterintuitive or surprising if you have in mind, especially dress states from, for instance, the James Cummings model, where indeed we have that if you keep increasing the atom-photon coupling strength, then you'll see the dress state frequency depart more and more from the atom's frequency. So what is going on here? It's going on that here what we realized is that these topological dress states belong to a general class of atom-photon dress states, and not necessarily we have topological systems in there. And we baptize this class of dress states vacancy-like dress states, and you'll see why in a second. So in order to characterize this class, you can consider rather a general Hamiltonian model for your photonic bath, not necessarily translational invariant. Only condition is that you have WA coupling, and okay, and the definition is quite simple. This is the general shape of a single photon atom-photon dress state, and what you define a vacancy-like dress state, or VDS in short, as one such edge state occurring at the same frequency as the atom. Now, through a two-line proof, you can see that this is entirely equivalent to saying that if you look at the photonic component of your dress state and photonic wave function, these exhibit a node at the atom's location. And you can also work out general formulas for these states in terms of the parameters of the bare photonic bath. And you can wonder now, when do these states occur? What are the criteria that have to be matched in order for these states to occur? Now take your atom coupled to your photonic bath, and call V the lattice site to which the atom is directly coupled to. Replace this site with a vacancy, and so you get now a photonic bath with a vacancy in place of the atom. Work out the normal modes of the photonic bath obtained this way, and which are represented by these spheres here. If you have one of such normal modes of the photonic bath with a vacancy in place of the atom occurring at the same frequency as the atom, then you see that according to a scheme which is in fact just the same scheme behind formation of a well-known dark state in atomic physics and also invariant state in quantum biology. You probably saw something this morning in the Suzanne Huelga's talk. There must be then in this case a superposition of your of the eigenstate of the photonic bath with a vacancy and your atom, which is certainly a stationary state of the full Hamiltonian. There are quite interesting examples that can be given, and I don't have time to discuss them, but I will just say that as far as we know for now, the most important consequence of this class of dress state is that this is the natural class that you have to consider if you want to study topologically protected dress state. And in fact, if you use the well-known Altran-Zimbayer classification of lattices and based on the symmetries of your bare photonic lattice, you can in fact map the problem into the problem where you have occurrence of an edge state given a vacancy by introducing a vacancy in your lattice. And this in fact works as a scheme, as a recipe to find new classes of such topologically addressed states. And I will show a couple of examples in a second. And this works as a kind of necessary condition. So can we go the other way around? Namely, you may ask whether, if I'm given a topologically protected dress state, will it always be a vacancy-like dress state falling within this class defined this way? And the answer to this question is yes, and this can be proven through symmetry arguments. And this shows that this VDS class is an important class to worry about in topological quantum optics, so long as dress states are concerned. We applied that, as I anticipated, to another two models. One is our 1D lattice, which is called Kreutz-Slader model, and then to the celebrated Haldane model, which is 2D. And in this case, you see that this dress state features the atom dressed by a single photon, which keeps orbiting around it. Good. Let me, before saying a few words about the other project on non-emission physics, let me just acknowledge my collaborators on this project, Luca Leonforte, my PhD student, and then Angelo Carollo, who is a researcher at the University of Palermo. Shall I have 5 more minutes? I think so.
Yeah, you have more couple of minutes.
Okay. Okay, let me just briefly sketch what we did regarding atoms coupled to an emission photonic lattice. Assume now that I'm given a photonic lattice which is lossy. So it's in fact coupled to some sort of superbath. And so far I've been discussing about the case where the structure of the photonic lattice, and this can be a structure admitting topological phases, results from the pattern of coupling strength between cavities. Now assume that I allow cavities to be lossy, so I have local losses in my photonic lattice, and the question is, what does this affect occurrence of atom-photon bound state? So you know that lossy photonic bath is commonly described, for instance, in quantum optics, not necessarily in quantum optics, through an effective Hermitian Hamiltonian. However, the standard case considered so far is that of uniform losses. Namely, you put the same loss rate on each lattice site. So this gamma n is a constant, and in this case, you get the same normal modes as the lossless photonic bath with the normal frequencies, which are just the same, but complex shift. Now, the question is, what if I introduce a pattern, a non-trivial pattern of local losses, which is not uniform? So in other words, what if the structure, introduce structure into my photonic lattice, not through coupling strength between cavities, but through a pattern of local losses? How does this affect atom-photon interactions? Okay, what we saw is, I'll just briefly mention what we saw in this project is we consider a case study, which is a photonic lattice called Lie model, which before interaction with the atom exhibits a photon chirality. And based on this photon chirality, this lattice exhibits the so-called non-emission skin effect, which is currently very popular in the literature, namely, under open boundary conditions, the bare photonic lattice features normal mode, which are all accumulated on the left edge in this case. Now, a couple atoms to the photonic lattice, what happens? Let me just discuss the most interesting point in the parameter space, so a critical value of the loss rate, and let me consider only two atoms. If I put the two atoms on nearest neighbor cell and excite only one of the two, you see that this guy will get de-excited, and meanwhile the other atom will get excited, absorbing part of the excitation emitted from the first atom, which is kind of partial state transfer. The state transfer is partial because the system is lossy, it's dissipation. What about the other way around? What if I excite the other atom and look at the excitation of the two? Nothing happens. If you excite the right atom, this guy will just decay and the first atom will remain unexcited all the time. So this means that we have here no reciprocal interactions between the two atoms. And notably, the chirality of these interactions goes from left to right. So the left atom with the right atom, not the other way around. And this is in contrast to the lattice chirality, which is from the right to left. Now, what if we place the two atoms in different cells? It turns out that any other choice for the atoms' locations will give zero interactions, as you can see here. But now, quite remarkably, if your lattice is subject to open boundary conditions and you place your atom on the two edges of the lattice, then again, you'll see a non-reciprocal interaction going on, just like in the case where they were nearest neighbors. So overall, this is the situation. You see that if the atoms are nearest neighbor, then you have this non-reciprocal interaction between them. In any other case, you get zero interaction, but again, if the two atoms are placed on edge cells, they will interact, just if somehow the lattice were not interrupted at this point. Okay, okay, you can generalize this to one atom per cell, and this was just what happens for a specific value of the loss rate. In general, you have a very interesting dependence on the loss rate, and you have interactions ranging from long range to exactly nearest neighbor. And we saw something which is kind of crazy, namely, you can ask, you can wonder, how do I get this effective Hamiltonian between the atoms? Under what boundary conditions for the lattice? And the answer is that the boundary conditions of the lattice are not important. So you get the same atom-photon effective atom-atom effective Hamiltonian, both in the case that the lattice is open and in the case that it's subject to periodic boundary conditions, as you can see here. And in particular, this means that if the open lattice is subject to open boundary conditions, this can...
sorry to interrupt. We're almost run out of time, so if you could wrap up.
No, I'm done. Okay. Despite the lattice does not fulfill translational invariance, you get it can mediate a translational invariant effective Hamiltonian between the atoms. Okay, let me just acknowledge the other people on this project: Federico Roccati, my PhD student, and Salvatore Lorenzo, Massimo Palma, Angelo Carollo. They're all based at the University of Palermo, where actually Federico Roccati is about to move to Luxembourg, and then Giuseppe Caloio from ICFO. So in conclusion, I identified a cluster of dress states which appear to have a key role in topological quantum optics. And I finally discussed how, by coupling atoms to photonic bath where you have structured losses, you can have occurrence of exotic atom-photon interactions. And finally, let me just advertise that we expect to have in the forthcoming months PhD and postdoc positions in our group. And with that, I thank you very much for your attention. And sorry if I made it a bit longer.
Thank you very much. So we can have a question. Are there any questions? So please, Andre, go ahead.
Okay, yeah, I may ask a question. Thank you very much, Francesco. I have a question about the first part of your presentation.
Yeah.
So for the eigenstates of the path, if we make them, I mean, they have a certain line width. How does this model depend on the line width of the path? So if we change the line width of the resonance of the path, will it be affected? And how?
Well, the bath
I mean,
the bath in the first part is lossless, so just the normal frequencies without broadening.
Okay.
But probably this may probably reply your question. I said that you see this physics, if you set your atom, you need to tune your atom with the frequency right at the middle of the band gap. This is rather robust. Yeah. You can see that in the weak coupling regime, if the band gap is large enough, this is rather robust to this condition.
Yeah, okay. Thank you very much. That's correct.
So thank you very much, Francesco, for the nice talk. So we will have a break now. And maybe I will leave the stage to Levent, the host, if there are announcements.
Thanks, Özgür, and thank you all the speakers of the session. I think we don't have any announcements to make, any pressing announcements to make. And we were debating whether we should close the Zoom meeting or not, and we decided to keep it going. But as you said, the next talk, which is the last talk of today and one of the plenary talks, is in half an hour. So feel free either to hang around here or in the Gather Town area if you want to talk to someone, and see you in about half an hour, less than that.
Can you enable the screen sharing?
Sure. Is it enabled?
Yes.
Okay.
It should be now.
Yeah, we see it. It's perfect.
Okay.
So let's wait for a few minutes. If it's okay. Let's start at exactly 5 o'clock here. The number of participants should increase.
Onur, should I go ahead and start recording on Zoom also? I think you are muted. I can't hear you.
Yeah, I said we can start. I'll make a brief introduction.
Mm-hmm.
Okay. Hi, everybody. I'm Onur Umcalılar from Mimar Sinan University in Istanbul. So welcome to the second and last plenary talk of our meeting to be given by Professor Stephen Gervin. It is probably needless for the experts in the audience, but especially for those of you who are new to the field, I'd like to give a brief biographical information about Professor Gervin. After completing his undergraduate studies in Bates College, Professor Gervin earned his PhD degree in theoretical physics from Princeton University in 1977, and he joined Yale University in 2001, where he is currently Eugene Higgins Professor of Physics and Professor of Applied Physics. Starting from 2007, he served as Yale's Deputy Provost for Research for 10 years. In 2020 and 21, he served as founding director of the Co-Design Center for Quantum Advantage. Throughout his career, Professor Gervin's research has focused on theoretical studies of strongly correlated low-dimensional many-particle systems, such as the fractional quantum Hall ones. Since coming to Yale, his interests have moved to atomic physics, quantum optics, and quantum computation. And along with his experimental colleagues, Professor Gervin co-developed circuit quantum electrodynamics, to which he will start introducing us in a minute. Before starting, I would like to remind the audience, including those following us on YouTube, that you can type your questions through the chat facility, Zoom, or YouTube as well. And I'll try to ask as many of them as time permits. And Professor Gervin actually said that students can ask questions, interrupt and ask questions as well during his talk. So as you prefer. So it's time to enjoy an illuminating talk. Please, Professor Gervin, the microphone is yours.
Thank you very much, Onur. It's a pleasure to be here, and I do encourage students to ask questions during the talk. If I say something that confuses you, it's better to ask and try to understand what's going on rather than wait until the end. So, I'm a theoretician, but I work closely with my experimental colleagues here at Yale on circuit QED, which is really applying the ideas of quantum optics to superconducting electrical circuits, where the role of the atoms is played by superconducting qubits, and the role of the laser from atomic physics is played by a microwave signal generator. So I'm going to try to give you an introduction to this topic and then one recent interesting quantum simulation experiment. So quantum electrodynamics is the study of atoms and electrons coupled to photons. And the essential piece of physics is that the vacuum, the electromagnetic vacuum, is filled with 0-point fluctuations of the electric field. And these 0-point fluctuations have many physical effects. For example, when you learn about the spectrum of hydrogen, you learn that there are quantized energy levels, stationary states that live forever. But in fact, they don't live forever. The excited states can decay towards the ground state or towards a lower state by spontaneously emitting a photon. And this is caused by the 0-point fluctuations of the electromagnetic field in the vacuum, making these excited states unstable to decay. And the hydrogen atom 2p state has a lifetime of about a nanosecond before it emits a photon. You can also have electrons which virtually emit and reabsorb photons. And these virtual processes cause shifts in atomic energy levels. For example, when you first study the hydrogen atom, you find out that the 2s and 2p levels are exactly degenerate. But when you include the fluctuations of the electromagnetic vacuum, you find that they're split apart by what's called the Lamb shift, a very tiny shift in frequency. The thing circuit QED is the analog of what's called cavity QED in atomic physics. And it's the study of what happens when you replace the continuous spectrum of electromagnetic modes with a discrete spectrum by enclosing the system, putting it between mirrors or enclosing it in a microwave cavity, where now only discrete frequencies of photon modes are allowed. And we use this effect, the change in the vacuum fluctuation spectrum, to enhance the lifetime of our superconducting qubits by a factor of 1,000. And we do so by arranging the frequency of the photons that are allowed in the cavity to be different than the frequency, the transition frequency of our artificial atom. So in atomic physics, you can do microwave cavity QED with Rydberg atoms. Here's a picture from Serge Haroche's Nobel lecture. He sends Rydberg atoms where the electron is in the, say, 50th circular orbit, and it goes into a region, a cavity that has a small number of microwave photons in it. It possibly makes a transition from the 50th to the 51st state. And then you detect that transition by measuring the state of the atoms after they have interacted with the photons. And depending on how long length of time they spent inside the cavity, they will undergo Rabi oscillations where they transition back and forth between what we call the ground and excited states of the qubit. Instead of measuring the state of the atoms, you can also have, in optical cavity QED, you have two mirrors. You drop a cloud of atoms through there. And these days, you can even trap those atoms in there. And you measure changes in the transmission of photons through the resonator, through this resonant cavity. So instead of measuring the state of the atoms, you measure the state of the photons to see how they are interacting. In circuit QED, we use, as I mentioned, microwave photons inside superconducting circuits and resonators, and we use artificial atoms, Josephson junction qubits. And these artificial atoms are very large in millimeter scale, and they give ultra strong photon atom coupling that lets us do nonlinear quantum optics at the level of 1 or 2 microwave photons. So here's a natural atom, the hydrogen atom, an angstrom or Bohr radius on a side. It has a characteristic transition frequency of 10 to the 15 hertz, a lifetime of a little bigger than a nanosecond. If you think of that as approximately a harmonic oscillator, it would have a Q, that is the frequency times the lifetime, of about 4 million. And the transition dipole moment, the ability, the matrix element to absorb a single photon, it corresponds to an electron moving a Bohr radius, which is called a Debye. And our artificial atoms are on a much different scale. They're electrical circuits made of superconducting aluminum cooled to near absolute zero. They're about 1 millimeter in size. Their characteristic oscillation frequencies for the charge going back and forth through this Josephson junction is in the microwave regime, gigahertz, 10 gigahertz. The lifetime can be 300 to 1,000 microseconds, even larger these days. And the corresponding Q is similar to that of hydrogen. But the transition dipole moment, the matrix element for coupling to electric field, is 30 million times larger because it corresponds to several Cooper pairs of electrons moving a millimeter instead of one electron moving an angstrom. So here's an electron micrograph of a sort of older version of the kind of qubit that we use. And the key element is the Josephson junction. It's a tunnel junction between one piece of aluminum and another piece of aluminum. You see it's just maybe 2,000 atoms on a side. And the two pieces of metal superconductor are separated by a thin oxide tunnel barrier, which you see illustrated schematically here. And it's the fact that Cooper pairs of electrons in the superconductor act like waves and are able to tunnel through this forbidden barrier to the other side that gives the artificial atom its anharmonic energy level structure. Without that, you would just have what's effectively an LC resonator, inductor, capacitor, electromagnetic resonator. But this tunneling property of the Josephson junction makes this act like a nonlinear inductor, and gives the instead of the evenly spaced levels of a harmonic oscillator, gives you unevenly spaced levels like in an atom, which is what we need to make a qubit. So here you see a close-up of a sort of modern version of this so-called transmon qubit. There's a piece of sapphire, very good insulator. There are two thin films of superconducting aluminum, and then a tiny Josephson junction connecting the two halves of this millimeter-long antenna. So you can think of this as an artificial atom with an atomic number of 10 to the 12, just a huge number of free electrons in here. So you would think that the spectrum would be even more complicated than the spectrum of uranium or some other heavy atom. But in fact, because it's superconducting, all of the electrons travel coherently in pairs as if they were in a single quantum state, and they move back and forth between the two sides of the antenna in a very simple way, which gives you a very simple spectrum, just that of an anharmonic oscillator. So here's a quantized energy level, a transition at, say, 5 gigahertz. And then the next transition is, say, 4.9 gigahertz. It's slightly smaller frequency. And so by choosing our frequency carefully, we can just cause transitions between these two levels and ignore other levels in the atom. And so the spectrum is actually simpler than that of hydrogen, even though there are a trillion electrons. There's no fine structure, no hyperfine structure. And the quality factor, as I mentioned, is comparable to that of hydrogen. But it has its own antenna built in, and so it's able to couple very, very strongly to the vacuum fluctuations, the zero-point electric field fluctuations of the microwave cavity. And that's how we take great advantage of this system to do nonlinear quantum optics in what we call circuit QED. So let's understand now how we gain quantum control of this hybrid system that consists of an empty box, a centimeter scale box surrounded by superconducting walls that trap microwave photons, and inside the box is one of these transmon qubits. That will focus on one particular electromagnetic mode of the box, and it's a harmonic oscillator. Its energy is given by some Planck's constant times the frequency times A dagger A, the number of photons in the oscillating mode. We're going to approximate this anharmonic spectrum of the qubit, we're just going to focus on the lowest two levels. And when you have a lowest two levels, you can think of that as an artificial spin 1/2. And this spin operator sigma z, which is -1 in the ground state and +1 in the excited state, this coefficient represents the energy omega q necessary to excite the qubit. And then the dipole coupling between the photons and the atom allow them to exchange energy. But if you work in what's called the dispersive regime, where the energy of a photon is not the same, this number is not the same as that number, the energy needed to excite the qubit, then this coupling only acts virtually or in second order perturbation theory. You can absorb a photon, but then energy is not conserved, so you quickly re-emit it. And when you calculate the effect of that, you get this dispersive term that you see here, some number chi, the dispersive shift, times sigma z times A dagger A. And I can give two different interpretations of this term. One is that the coefficient of A dagger A, which I call the cavity frequency, now depends on whether the qubit is in Z is +1 or -1. So the cavity frequency depends on the state of the qubit. Or I can say, no, it's the coefficient of sigma z, which is the frequency of the qubit, now depends on how many photons are in the cavity. And atomic physicists call that the light shift. And because of the very strong coupling of our atoms to the photons, this number here can be hundreds of thousands of times larger than you would get in ordinary atomic physics. And this number can be, 3,000 times larger than the line width and the dissipation rates of either the cavity or the qubit. So that's where all our ability to control things comes from. In addition to this Hamiltonian, we can turn on a microwave drive, which will excite, remove, and add and remove photons from the cavity through this term. And we can turn on another drive, which at the qubit frequency, which can excite and de-excite the qubit. And so this Hamiltonian gives you what's called universal control. You can make any quantum state in principle using this Hamiltonian and these controls. And in particular, you can displace the cavity. You can excite the oscillator in a way that depends on the state of the qubit. And you can rotate the qubit in a way that depends on the state of the cavity. And I'll explain more about this. So here's an example of universal control. So here's a cavity, and I can have a drive that excites the oscillator mode that's inside this cavity. And I can have another drive which excites the qubit, which is coupled into the cavity here. And I can start with 0 photons and the qubit in the ground state. And I can try to put exactly 6 photons in the cavity and leave the qubit in the ground state. And I do that by applying some complicated electromagnetic pulse to the qubit and a different one to the cavity. And I calculate this, the needed pulse from numerical optimization techniques, knowing the Hamiltonian. And here you see a plot of the photon number in the cavity. And it starts at 0 and it rises up and it wiggles around. It splits into different values. And then all of a sudden at 500 nanoseconds, all the probability collapses onto n equals 6. And here you see the photon number probability distribution. is exactly 6. And here you see a plot of a measurement of what's called the Wigner function. It's a quasi-probability distribution in phase space. This is the position of the oscillator, the electric field. This is the momentum of the oscillator, the magnetic field in the cavity. And you see it's completely rotationally symmetric. And that's just an illustration of the number phase uncertainty principle. We know the number exactly, so we're completely uncertain what the phase of the electromagnetic field is. And we have a way of making these measurements, which I won't go into, but it's based on our ability to measure the parity of the photon number. Is it even or odd? And I'll explain how we do that later. So here's some other example of our ability to control. This is the so-called Gottesman-Kitaev-Preskal error correction code states that you can make in both superconducting cavities and in trapped ion systems. And it's essentially a kind of Schrodinger cat that lives in 35 different places at once in phase space. And you can use this universal control to build these beautiful, complicated superpositions of different numbers of photons in the cavity. Okay, so that's illustrations of the kind of control you can achieve, which is very, very much easier, I would say, than in traditional quantum optics because of the strong dispersive coupling. Now, in addition to creating states, we have to make measurements of them to see what we have. And we're going to use the same Hamiltonian to do that. So here's an example of a measurement. Is the photon number equal to 1? Yes or no? So that question yields 1 bit of information. And the way we answer that question is we map the answer onto the state of the ancilla qubit that's coupled to the cavity. We could ask, is it 1 photon, yes or no? Is it 13 photons, yes or no? This is not a very efficient way to find out how many photons there are. Let's say there are 256 possible photon numbers. And if you say, is it 0? Is it 1? Is it 2? Is it 3? The answer will be no most of the time. But still, so it's inefficient sampling, but you can still get the answer. Now, and I'll illustrate this first, and then I'll show you a more efficient method. So how do we do that? Well, here's the circuit. The cavity is in some superposition of different numbers of photons. Our ancilla qubit is in the ground state. And I'm going to carry out a unitary rotation of the qubit by an angle that depends on how many photons are in the cavity. And then I'm going to measure the qubit to see if its state changed. So in particular, I'm going to rotate the qubit by an angle of pi around the x-axis. I'm going to take it from 0 to 1 if and only if there are exactly m photons in the cavity. Otherwise, I'm not going to rotate it. So if I see the qubit change state, I know there are exactly m photons in the cavity. Well, that works in principle, but how do I do it in practice? Well, I use this same Hamiltonian, and I noticed that the frequency of light, of microwave light, that you need to flip the qubit from ground to excited shifts by 2 chi for each photon that I add to the cavity. So here's the spectrum of the qubit. If there are 0 photons, the a spectral line is at this frequency. If there's one photon, it's here. If there's two, it's here. If there's three, it's here. So if I send in a microwave pulse, a pi pulse, which just has the right amplitude and frequency to flip the qubit from 0 to 1, it will be on resonance and will flip the qubit if and only if there's exactly one photon in the cavity. If there are 2 or 3 or 0, this photon will not have the right energy to be absorbed. And so that's how I can execute this. Another thing I could do is shine 2 microwave tones, one at this frequency, one at this frequency. And that will answer the question, is the photon number equal to either 1 or 3? It still has 1-bit answer, yes or no. But now if you see the qubit flip, you don't know whether it was because this photon was absorbed or that photon was absorbed. Either n equals 1 or n equals 3 will cause the same answer. And you can extend this by applying any tones at any photon number frequency you want to measure any arbitrary binary valued function of the photon number. So I can have a string, a binary vector, a string of zeros and ones, and it's 0 if I'm not shining a photon at that frequency, and it's a 1 if I am shining a photon at that frequency. So for this case, C sub 1 and C sub 3 would both be 1. And this measurement would tell me that either there was 1 photon or 3 photons, but I don't know which. I can extend this to a more complex sequence of gates and measurements, which will be a very efficient binary search to locate the photon number. So basically, the first microwave pulse here, I apply a tone that that flips the qubit if it's in the upper half of the available photon number between 0 and 15. So the top 8 numbers. Then I make a measurement, then I apply a tone which gives me another bit of information in the binary representation of the photon number, and so on, down to the last one, which tells me whether the photon number is even or odd, because I'm applying a tone that will flip the qubit if the photon number is 1, 3, 5, 7, 9, 11, 13, or 15. And won't flip it if the photon number is even. So by combining together the results of all these measurements, I get 4 bits of information that tell me whether what is the value of the photon number between 0 and 15. And this, if I went through and measured, are you 0, are you 1, are you 2, are you 3, that search is expensive because most of the time the answer is no. But here I get a useful bit of information in the binary representation of the photon number with each measurement. So it takes only logarithm of the maximum number of photons in the distribution, number of circuit depth, number of gates and measurements. So it's exponentially more efficient. So what can we do with this? Well, I can use this to do a hardware efficient quantum simulation of an interesting physical model that contains bosons. So in particular, we're going to do an experiment simulating the optical spectrum of a vibrating molecule. And the spectral line strengths are determined by what are called Frank-Condon factors. And it turns out that this is can be mapped onto what's called a boson sampling problem, where you have many, an interferometer with many ports, and you put in a specific number of photons at each port, and there's interference, and then you measure where the photons come out. And I'll explain how this works now. So I'm going to this is going to be very efficient because I'm going to use microwave bosons to simulate mechanical bosons, the mechanical vibrational modes of a triatomic molecule. So we're going to focus on two modes, the symmetric stretch mode, where the two, in this case, hydrogen atoms vibrate in phase, and the length of their bonds gets longer and shorter, and the antisymmetric bending mode, where the opening angle between the two hydrogens, the bonding angle here, oscillates in time. And these are mechanical oscillators, and we're going to simulate them. We're going to represent their quantum states by the quantum states of these two microwave oscillators, these resonators, one for stretch and one for bending. And we're going to control and manipulate the quantum states by using these ancilla transmon qubits. And we're going to carry out a simulation that will tell us the spectrum of these molecules. So the chemistry experiment works like this. It's a photo emission. I come in with an ultraviolet or X-ray photon, and I eject an electron from one of these bonds. So it breaks the reflection symmetry that you have here that makes this mode symmetric and this mode antisymmetric, because it removes the electron from only one of the bonds. That changes the bond length and the spring constant and causes the molecule to begin vibrating. And the way you describe this, and then that leaves behind some vibrational energy in the molecule. And that energy lowers the energy of the photoelectron, which is ejected. And so you can detect by measuring the energy of this electron how much vibrational energy was left behind in the molecule. And sometimes it's 3 quanta and 2 quanta, 5 quanta, different in each of the modes. So the way to think about this is that the chemical bonds form kind of springs, maybe nonlinear springs, and define a potential energy surface that the nuclei slowly move on because they're much more massive than the electrons. And it's a two-dimensional potential energy surface. There's a coordinate for the bending mode and a coordinate for the stretching mode. And this potential well has quantized energy levels. And what happens when you suddenly eject an electron, you change the potential energy surface, but not where you are, because the nuclei are heavy. But now you project this state onto a superposition of excited states in the molecule. And you have some probability of leaving behind this many quanta, and some probability of this, and some probability of this. So here's the first generation experiment. We obtain the nuclear potential energy surface by solving the chemical bonding problem on a classical computer using various approximations. Then we approximate that potential energy surface as quadratic. That is, we approximate the mechanical vibrations as harmonic oscillators, at least in this first experiment. We have a new experiment just come out where we go beyond this. But we allow for the two potential energy surfaces to have different vibrational frequencies they're displaced from each other, they're squeezed, the spring constants change, and we allow the symmetry axis of the surface to rotate because you break the symmetry in the molecule by removing, you break a bond on only one of the two bonds. And then suddenly the electron is removed and you have to perform a unitary transformation between the eigenstates of the old potential energy surface and those of the new potential energy surface. So that's what our quantum computer, our quantum simulator is going to do. So in order to do this simulation, you need some bosonic modes. So we're using microwave cavities. You need various Gaussian operations, such as beam splitters, squeezing, which is just, shrinking the uncertainty in position to increase the uncertainty in momentum. And you need displacements, all of which we can do. And you need non-Gaussian state preparation. You need to be able to make Fock states of 3 photons or 7 photons or whatever in each mode. And then you need to be able to measure how many photons there are in the modes after you've changed the Hamiltonian. And I just showed you a few minutes ago how we do that. So these two things are, this was originally proposed to be done in optics, and it is being done in optics, but it's much harder to do squeezing and number resolve detection in traditional quantum optics than it is using our circuit QED. So here is the program or the gate sequence for our little quantum computer. We have 2 cavities, Alice and Bob, and 3 different transmon ancillas.
Sorry, Professor Gervin.
Yes.
There is a question, I guess, from Levin.
Okay,
sure.
Quick question, if I may interrupt. Could you say again how these bending and stretching modes map to the boson sampling analogy?
Sure. So these nuclear, the vibrations are approximately harmonic oscillators, mechanical oscillators. And you can have 1 or 2 or 5 quanta of excitation in this stretch mode, and 3 or 4 or 7 quanta in this bending mode. And then I'm going to, if there are 3 mechanical quanta in this mode, then I will put 3 microwave photons in this mode. And if there are 7 mechanical quanta in this mode, I will put 7 photons in this cavity. Does that help?
Thanks, yes.
Yeah, the frequencies are completely different and so forth, but that doesn't matter. You can sort of scale those differences away. Okay, so you initialize the qubits in the ground state and the cavities into Fock states with, say, 0 photons here and 0 here, or 1 here and 3 here. You carry out this unitary transformation that changes the basis from one potential energy surface to another. Then you check, there are certain checks we do to make sure that no errors occurred. And then we make a measurement of the number of photons in each cavity mode. And that represents the number of mechanical vibrations that were excited when the chemical bond was broken. And the transformation that we have to do involves squeezing the first cavity, squeezing the second cavity, doing a rotation of the potential energy surface by forming a beam splitter between the 2 cavities that mixes them coherently, and then anti-squeezing and anti-squeezing, and then displacements and displacements. And you can show that by doing all the correct gates here, you can simulate this chemistry experiment faithfully. So here is a theory versus experiment. This is for water, photoionizing to water plus and an electron. And this scale is the energy, the vibrational energy left behind in the molecule, taken away from the electron. The black lines are the ideal spectra, okay, calculated theoretically because from our model. It's easy to do because it's a very simple model. And then I told you there were two different ways to count how many photons are in a cavity. One is just slow but efficient sampling. You ask, is there 0? Is there 1? Is there 2? Is there 3? And you take thousands and millions of shots and you get the average probability that some certain number of photons was in cavity A and a certain number in cavity B, and then that tells you the height of this this spectral line. We know the frequencies and the modes, so we know energy 7 Alice quanta and 3 Bob quanta would correspond, let's say, to this particular energy left behind in the molecule. And you can see a fairly complicated spectrum and quite good agreement between the experimental results and the height of the lines. There's also this more efficient sampling where we do 4 consecutive quantum non-demolition measurements and get the 4 bits that represent the photon number. It's 32 times faster, but it's a little bit less accurate, as you can see. So how do we measure how close our experimental probability distribution is to the theoretical one? Well, you can measure that what's called the L1 norm distance between the exact and experimental distributions. So this is the probability experimentally that there are I quanta in the Alice mode and J quanta in the Bob mode, and this is the theoretical value. And you just take the sum of the absolute values of the differences. And for our single bit sampling, it's about 5%. And for our efficient sampling scheme, which is exponentially faster, it's about 15%. Here's some other spectra. I think this is ozone starting with a different state. But I want to emphasize that typical photodetectors, if you were to do this in ordinary optics, the photodetectors are not number resolving. They can tell you there were 0 photons or not 0, but they can't tell you exactly how. It's difficult to know exactly how many photons there were. And also they're destructive. When they eat up, they consume the photons, so you can only measure them once. With our quantum non-demolition boson number sampling, where we make 4 measurements to see what the frequencies of what the photon number is, we don't destroy the photons. We just flip an ancilla qubit if the photon number is present. We're able to do this much more efficient boson sampling. So we have 256 different photon states, between 16 in each cavity. And we make very efficient measurements. We get 4 bits of information on the photon number in one cavity and 4 bits in the other cavity. And that's a huge advantage in terms of speed. So I also want to emphasize that if you tried to do this simulation on a traditional qubit-based quantum computer, well, to get 8 bits of information about the photon number, you'd have to have 8 physical qubits, and more than one to carry out that unitary transformation from one basis to the other, you would need more than 1,000 gates of very complicated multi-qubit gates, which is well beyond the capability of any existing traditional quantum computer, but was relatively simple for our quantum system, which consisted of only 3 qubits and 2 microwave oscillators. And the benefit of having actual bosons in your quantum computer is that they're very good at simulating models that contain bosons, whereas qubits are very inefficient for simulating bosons. It turns out that simulating bosons is at least as hard, maybe harder in some sense, as simulating fermions, even though there are no minus signs. So for the future, we're extending this to anharmonic oscillators, simulating those. We'll have a paper coming out soon. And as a theorist, I'm fantasizing about further in the future when we could simulate interesting, strongly correlated many-body states for bosons. For example, one of my favorite things is the fractional quantum Hall effect. It's never been seen for bosons, only electrons. So could we build a lattice of microwave resonators and convince the photons to act like charged particles moving in a magnetic field? If we could do that, then we could see fractional statistics of photons and even non-abelian statistics, and it would be extremely interesting. And we have all the pieces in place to do it. We could, in principle, we could build an array of microwave resonators, and we could have beam splitters which will allow the photons to hop from here to here to here to here. And we have a way of adjusting the phase of this hopping matrix element so that when the photon goes around a closed loop, it picks up a non-zero phase as if it were a charged particle moving in a magnetic field in a vector potential, and it picks up a Harona-Bohm phase. So we could convince the photons that they're charged particles hopping on a lattice in a magnetic field. And we can also have the photons interact by applying certain gates that we've developed called snap gates that would impart like a Hubbard, boson-Hubbard model repulsion among the photons. So here you see an example of, we have 2 cavities and we put a photon in one and we swap it back and forth, back and forth, back and forth between the 2 cavities. We need faster gates, longer coherence times. We need to be able to control the phases of all these beam splitters in a very large array, but that technology is coming. We need to develop it in order to build any kind of quantum computer, large-scale quantum computer built on this technology. So that it's almost ready, but the experiment could be done, I think, in a few years from now. So I'll stop here and thank the Sholkoff Lab, and in particular, Chris Wang and Jacob Curtis, who did the molecule simulation. We collaborated with actual chemists who taught us about molecular spectra. And Ike Chuang helped us estimate how much harder this calculation would have been to do on a qubit-based computer. And I also showed you some data on GKP states from the Devray lab with whom I also collaborate. So I'm stopped there, and I'm happy to take questions. Thanks.
So yes, there's a question from Imre Özbay, please.
Professor Gervin, thank you very much for this enlightening talk. I'm wondering about the mapping between actual chemical results or calculations and the quantum computer calculations. So how do you map the result? You said you just scale them. Is this a simple linear operation, or how do you do it? Thank you.
Yeah, it's pretty simple. So it doesn't actually matter. So if I know the mechanical frequency of the stretch and bending modes, and I know how many quanta there are in each mode, then I can calculate the energy. I know that because I have solved the frequencies on a computer separately from this experiment. So I know the locations of these lines. Now, of course, the locations, the energies in the microwave oscillator are completely different. But that doesn't matter. It's just the probability distribution that when I break one of these bonds, and I create 3 quanta in one mode and 5 in the other, that's all I have to get right. Because I can just rescale the microwave oscillator frequency trivially until it matches this. The location of these peaks is known. It's only the probability. So this peak will correspond to so many photon mechanical quanta in one mode and so many in another. I just have to get that part right to tell me the height of this line, the probability of this line. It's a trivial rescaling to get the frequencies correct. Does that help?
Yes. So it's a simple yes. Thank you.
Yep.
So are there other questions? There might be one in the chat. From Atalay again. So there was an exponential gain with mapping to boson states. My question is, can it be worthwhile to try and find a quantum mechanical formalism which has the property of mappings between systems is easier?
Let's see if I understand the question. So
can you see the question?
Let's see if I can see the question.
To read it yourself.
Chat.
Oh yeah, I can repeat.
So in order to simulate a boson system, there's some large number of states that the system can be in. I can map those onto a large number of states of qubits, or I can map it onto the corresponding states of some other bosons, in this case, microwave bosons. And it turns out that very simple things like the operator to create a photon, a dagger, is extremely hard to represent in qubits. You have to flip many, many qubits in a complicated way. Whereas it's a kind of native operation that's straightforward to do if you have actual physical bosons. So that's where we get efficiency in simulating bosons is by having bosons in our computer. I'm not sure if I'm answering your question.
Perhaps Atalay can write back to us if you. Okay, so there are two more questions. First, Sina, please go ahead.
Hi, thank you for the nice talk. Yeah, I guess it's like a follow-up question to the previous question in a sense, or your answer basically. So is it true then, if I have qubits and I have a this kind of parity dependent, or like the an energy shift dependent on the different digits in the binary expansion of a number, like is that really the main thing, that if I have a interaction like in, for instance, Rydberg atoms or something, where I could do like parity measurements, or I can do similar, if I can use the different energy shifts, basically, if I can use the frequency bandwidth in this way, is it going to be efficient, or is there something else?
I'm not sure. It might be possible to do something. It's not so difficult. Suppose I wanted to represent a harmonic oscillator, I could have n qubits, let's say 4, and the frequency of the first one could be 1, and the frequency of the second, the transition energy could be 2, and then 4, and then 8. And then they would have, their total energy would just be given by the binary number that those 4 qubits represent. So that's not so difficult, I guess, in principle. But if you will look at, suppose I want to destroy 1 photon. I want to change from 15 photons to 14. So it turns out that, so 15 photons is all 4 bits are 1, and then 14 photons, I just have to, remove 1. But if you look at the arithmetic, sometimes many bits flip when you do arithmetic, when you lower the number by 1. And which ones to flip depend on what number they represented. So it's a very complicated multi-bit gate, which is expensive and right now impossible to do with qubits.
Oh, I see. Yeah, I can maybe think about it a bit more.
Whereas if I actually have an oscillator, it's easy to apply A plus A dagger and A minus A dagger and so forth operators.
I see. Yeah, I was also thinking maybe, like contrary to your example, maybe there's a separate like cavity-like qubit whose energy shift depends on, so it's not the energies of individual qubits, but the energy shift of the cavity in a sense, or like the energy shift of the sensor qubit.
You might be able to arrange such a Hamiltonian. So I don't think that's where the main efficiency gain comes from for us. I think it's the squeezing and displacements are very easy to do if you actually have bosons, and very hard to do if you have qubits.
Yeah, perfect. Yeah, thank you.
Yeah, thank you.
Okay. Shakirullah, please.
Okay, thank you very much for such a nice talk. My question is, you have applied a phenomenon of boson sampling with number states. We know that boson sampling is computationally efficient, but could one apply Gaussian boson sampling, for example, with squeeze states? Because I think Gaussian boson sampling is more efficient than boson sampling. So it would be, and from my point of view, it would be better if you use Gaussian boson sampling instead of boson sampling.
So it's not, I think you don't mean efficient, I think you mean more greater complexity for classical simulation. Is that right?
Yeah, of course, yeah.
Right. Yes, that's right. So if you have an array of beam splitters, and you put in coherent states, it's simple to calculate the coherent state amplitudes that come out on the other side. It's the beam splitters, it's just simple algebra. But if you have, you need to even with, if you want to measure the number, you have to do something non-Gaussian. If you want to measure the number of photons in the output, that's where it's computationally hard classically. And I think it's somewhat harder if you use squeeze states because there's a bigger range of photon numbers. But you need something non-Gaussian to make it classically hard problem. So people sometimes ask me, could we do a quantum supremacy experiment this way? Well, yes, in principle, but you have to get to of order, I don't know, 50 oscillators with hundreds of photons before it becomes classically hard, really hard for modern computers. So this is not, this will not do that in the near future.
Okay, thank you very much.
Sure, thank you. Good question.
So there is one request-like question from Ceyhun Bulutai. Steve,
yes,
are you ready?
Right, so he's just asking about optomechanics. So there's a lot going on in optomechanics where you have mechanical oscillators coupled to microwave or optical light. Some of the things that I'm excited right now are experiments by my Yale colleague, Jack Harris, who is using liquid helium, superfluid helium, as the mechanical medium. So he has two mirrors that trap the light, but they also trap the mechanical vibrations, the phonons, the sound waves in the helium. And he can get very strong coupling between them. And he recently posted a paper measuring high order correlation functions in the numbers of phonons that he detects. And I think there's a lot of interesting possibilities there for future experiments, including, because the phonons have a very long lifetime, including remote entanglement and things like that. So that's one thing I'm interested in. In the microwave domain, there are experiments going on, John Teufel and people at Gila in Colorado, where they're trying to do entangle different mechanical oscillators with microwaves, and also trying to do conversion of microwave photon states to telecom optical wavelengths, which would be very powerful for quantum communication.
Okay, I see two raised hands.
Aaron can go ahead.
Okay, sure, then I'll go ahead. I wanted to ask about this parity measurements that you made earlier in the talk. I think you're showing the screen now, actually.
Yes.
When you make sequential measurements on the qubit, do you have to deal with some kind of back action on the cavity?
Absolutely.
Or do you pre-prepare and do like tomography style, or?
Yeah, so if I apply this gate, so I put a microwave tone which will flip the qubit if the photon number is 1, 3, 5, 7, 9, 11, 13, or 15, then if the qubit flips, I don't know what the photon number is, but I know that it's odd. So then, of course, there's a major back action on the cavity, namely all of the even photon number amplitudes get set to 0 if I find that it's odd. If I had, let's say, coherent state where I have a Poisson distribution of photon number, and I ask, is the photon number equal to 3, yes or no? Then if the answer is yes, that state collapses to photon number 3 and nothing else. If the answer is no, then all the other amplitudes are unaffected, but you remove the amplitude that it was 3, and then you have to normalize it. So there's a very interesting non-trivial back action on the cavity that can completely or partially collapse the state depending on the measurement result. Is that what you were asking about?
Basically this, and the fact that since you make, it looks like you make sequential measurements, like after some interaction. And so there's this, I guess that you have to take into account this effect when you make the next interaction to prepare for the next measurement somehow.
Yes, so so I'm going to, I didn't emphasize this, but these are quantum non-demolition measurements. And I'm going to keep the qubit alive for 4 operations and 4 measurements. Everything is coherent. So in the first measurement, I collapse the state into, I remove all the amplitude that the photon number is in the upper half of the range or the lower half, depending on the measurement result.
And so you sort of just sift through the amplitudes.
And then you say, let's say it's in the upper half. Then I collapse it onto the upper or lower half of the upper half.
Yeah.
And then the lower and upper half of that. And finally I get, down to, is it even or odd? And so finally I have collapsed the state to a single photon number.
Great.
It's pretty weird.
It's pretty nice though.
Yeah.
And also for state preparation kind of thing, it's quite cool.
Exactly. Yeah. And so I get a result every time, I get 4 bits of information from which I can reconstruct the photon number that I measured. So it's very efficient. It's exactly binary search, is it in the first half of the phone book or the second half, etc.
Okay, cool. Thanks so much.
Yeah, sure.
So there is one more raised hand. Perhaps we can get that too. Imre?
Yes, I think I'm going to take my question back, but just to make sure I get it correctly, we are sampling from the cavity, right? We are trying to determine the number of photons in the cavity, correct?
Yes.
Okay, I was just going to make a wrong comment, but I take it back. No worries. Thank you.
Yeah. So what's interesting is, remember, I'm not absorbing the photons to see if they're there. I'm using the fact that they shift the frequency of the qubit. And so if the qubit flips, when I apply a certain frequency, I know what the photon number was, but the photon is still there. So I can I can still do further measurements to refine my knowledge of the exact photon number by doing this binary search. It does, however, require that everything stay coherent through the longer time that it takes to do all 4 of these operations, which is why it's 32 times faster, but it's somewhat less accurate than just, slowly going through and asking, is it 1, is it 2, is it 3, is it 4, in separate experiments, one repeated millions of times.
So how tired are you Professor Gerben, can I ask one last question?
Oh, please, please. I love questions. So thank you. These have been good.
Okay, so I will ask something about the last part of your talk about fraction quantum Hall effect. So I saw a recent paper of yours on the archive, which is related to the dissipative stabilization of fraction quantum Hall states.
Yes.
Saying that it takes considerably longer time to prepare a fraction quantum Hall state compared to a multi-insulator state, perhaps due to fractionalization effects.
Yes.
So how bad it is?
Well, yeah.
Are there really prospects of getting, for instance, non-abelian states?
Right. So the basic idea is that, you know, people, Bob Laughlin and, you know, people who've studied the fractional quantum Hall effect for electrons, you don't have to worry about losing any of the electrons. But I showed you that these cavities and qubits, you know, have finite lifetime, so you might lose one of the bosons. And that's a challenge for this kind of simulation. And there are ways to engineer the bath, the environment, so that you can irreversibly, if you lose a photon, put a photon back and repair the state. It's a kind of error correction, if you will. But once you lose a photon, it's possible that it will split into two fractional charges, two half photons for the, depending on the particular quantum Hall state. And once they've separated from each other, then there's no room to put a whole photon into a space that only holds half a photon. And so it takes a long time before those two come back together and you can refill. That's the basic idea of our paper. So it's going to require an ability to if a photon is lost, to very quickly refill it from the bath. But there's a speed limit on how quickly you can do it, which is set by the excitation gap above the many-body state. So it's a significant challenge, but I think it means that we will be able to make such many-body states, but they will have a few, you know, more defects than you might have expected from simple estimates.
So is it realistic to expect some topological quantum computation using these systems?
I think that will be very difficult. I mean, I can't imagine, it will not happen in the near future. If we can learn to control extremely high quality cavities, it may be possible. So you can build microwave cavities that have lifetimes of 2 seconds. People who, you know, who build particle accelerators with superconducting cavities can do that. But the reason they have long lifetimes is they're very big. So the photons take a long time. They spend most of the time in vacuum, and they don't spend a lot of time bouncing off the walls, which is where the absorption occurs. Well, if they're very big in volume, that means that our qubits will now have trouble controlling them, because the photons won't travel near the qubits very often either. But if we could solve that problem, then I think we could have very long-lived bosons that in which you could imagine doing topological computation. But whether we can control the boson states strongly and rapidly is a pretty big challenge, because the more strongly you couple the qubits to them, the less likely you'll still have a 2-second lifetime, because the lifetime of the qubits is much worse than the lifetime of the cavity. So I'm pretty pessimistic that this can be done anytime in the near future. But boy, it would be a fantastic possibility if we could do it.
Okay. So I think there are no questions. Thanks a lot for this beautiful talk, Professor Gervin. And I think it was a fantastic first day. So good evening, everybody, and see you tomorrow at 10:20 Istanbul time.
Thank you all for your excellent questions. I enjoyed chatting with you.
Thanks a lot, Professor Gervin.
Yeah. Bye-bye.
Bye.